Welcome back to Deep Space Dreams, where we drift through the deep past, one story at a time. Tonight, we're going on a slow, soothing journey into one of the most intriguing cosmic mysteries of recent years. A mystery about a visitor that appeared from the depths of space, grew brighter with each passing day, and then quietly dissolved before our eyes. Was this ancient traveller, known as Comet 3I/ATLAS, somehow watching our planet during its brief passage through our solar system? It's a question that invites us to consider not just the nature of comets, but our own relationship with the cosmos that surrounds us. As always, I hope this video helps you drift off gently, or at least helps you put your worries into perspective by zooming out a few 100,000 years. Of course, there's a small risk that it might be too interesting and keep you awake. But if that happens, well, at least you'll have learnt something fascinating along the way. Before we float off into the past together, I'd love it if you gave this video a like and maybe even subscribed if you haven't already. It really helps this sleepy little channel grow. I'd also love to know where you're watching from and what time it is for you right now. Let me know in the comments. It's always such a joy to see our sleepy history community scattered gently across the globe. Now settle in. Get comfortable. You don't need to remember any of this. You don't need to take notes or stay alert. Just let the words wash over you like whispers on the wind. And as we begin this gentle voyage into the vast unknown, remember this video is for educational and relaxation purposes only, and is not intended as medical advice. Ready? Let's begin. In the early months of 2020, while the world was turning its attention to earthly matters, something extraordinary was happening in the cold depths of our solar system. A faint smudge of light, barely visible even to our most powerful telescopes, was beginning its final approach toward the Sun. This was Comet C 2019-Y4, better known as ATLAS, named after the Asteroid Terrestrial Impact Last Alert System that first detected it on December 28, 2019. But perhaps detected isn't quite the right word. Perhaps we should say that Atlas revealed itself to us, like a secret that had been kept for millennia was finally ready to be told. Consider for a moment the profound silence of space, not the kind of silence you might experience in a quiet room, or even in the deepest forest at night. This is a silence so complete, so absolute, that sound itself cannot exist. In this perfect vacuum, Comet Atlas had been travelling for thousands, perhaps millions of years, making its way from the outermost reaches of our solar system. It moved through this silence not with purpose as we understand it, but with the inevitable certainty of gravity's gentle pull. Every second of every year of every century it fell slowly toward the Sun, following an orbit so vast that human civilization rose and fell many times over during just a portion of its journey. The comet first appeared to us as nothing more than a mathematical whisper in the data streams of our automated sky surveys. These patient electronic eyes scan the heavens night after night, comparing images, looking for anything that moves against the fixed backdrop of stars. When Atlas first appeared in these images, it was magnitude 19.6, which in the language of astronomy means it was about 398,000 times fainter than the faintest star visible to the naked eye. To put this in perspective, imagine trying to spot a single candle flame from a distance of 3,000 miles away, through a fog on a moonless night. That's approximately how faint this cosmic visitor was when we first noticed its approach. But here's where our story takes its first intriguing turn. As astronomers calculated the orbit of this newly discovered comet, they realized something remarkable. Atlas appeared to be following nearly the same path as the Great Comet of 1844, a spectacular visitor that had graced Earth's skies 176 years earlier. Could these two comets be fragments of the same ancient parent body that had broken apart thousands of years ago? Were we witnessing a family reunion of sorts, played out across centuries of human time but mere moments in the life of the solar system? The mathematical poetry of orbital mechanics tells us that comets don't simply wander randomly through space. They follow precise elliptical paths, drawn by the Sun's gravity into long looping orbits that can stretch far beyond the orbit of Neptune, out into the mysterious Oort cloud. This vast spherical shell of icy bodies surrounds our solar system at a distance so great that light from the Sun, travelling at 186,000 miles per second, takes over a year to reach its outer edge. From that incomprehensible distance, Atlas began its fall toward the inner solar system, accelerating gradually as the Sun's gravity grew stronger with each passing year. As winter turned to spring in 2020, something beautiful began to happen. Atlas was brightening, and it was brightening fast. Much faster than astronomers had initially predicted. By late March, the comet had increased in brightness by a factor of 4,000 in just a matter of weeks. Suddenly, what had been an object visible only to professional telescopes was becoming accessible to amateur astronomers with modest equipment. The excitement in the astronomical community was palpable, though expressed in the measured tones of scientific papers and cautious predictions. Some models suggested that Atlas might become visible to the naked eye by May, possibly even rivaling Venus in brightness. Imagine that for a moment. A visitor from the edge of the solar system, shining in our evening sky bright enough to cast shadows. But what exactly was brightening? What is a comet, really? To understand Atlas and its journey, we need to drift deeper into the nature of these cosmic wanderers. A comet is, in essence, a time capsule from the birth of our solar system. About 4.6 billion years ago, when the Sun first ignited and the planets were still forming from a swirling disk of gas and dust, not all of the material coalesced into these larger bodies. Some of it, particularly in the cold outer reaches of the forming solar system, clumped together into smaller bodies, mountains of ice mixed with rock and dust. These became the comets, preserving in their frozen cores the original ingredients from which our entire solar system was built. The nucleus of a comet, its solid core, is surprisingly small. Even a comet that appears spectacular in our sky might have a nucleus only a few miles across. Atlas was estimated to have a nucleus perhaps 3 to 6 miles in diameter, roughly the size of a small mountain. But this mountain was made not of solid rock, but of a fragile mixture of ices, primarily water ice, but also frozen carbon dioxide, methane, and ammonia, all mixed with dust and small rocky particles. Astronomers sometimes describe comets as dirty snowballs, but perhaps a better analogy would be a very loosely packed snowball made from snow that's been mixed with ash and pebbles, held together by the weak gravity of its small mass and the cold that has preserved it for billions of years. As Atlas fell toward the Sun, something fundamental began to change. The increasing warmth of solar radiation began to sublimate the ices in its nucleus, transforming them directly from solid to gas without passing through a liquid phase. This process, which seems almost magical when you think about it, creates the comet's distinctive features, the coma and the tail. The coma is an atmosphere of gas and dust that surrounds the nucleus, growing larger as the comet approaches the Sun. By the time Atlas was near its brightest, its coma had expanded to be nearly 450,000 miles in diameter, more than twice the distance from Earth to the Moon. Imagine that. A gossamer sphere of gas and dust, wider than the orbit of our Moon, all emanating from a nucleus you could walk across in an afternoon. The tail, or more accurately tails, since comets typically have two, stream away from the Sun, pushed by solar wind and radiation pressure. One tail is made of dust particles that reflect sunlight, often appearing yellowish or white. The other is composed of ionized gases that glow with their own light, typically appearing blue or green. These tails can stretch for millions of miles, yet they contain so little material that they're less dense than the best vacuum we can create in laboratories on Earth. If you could somehow collect all the material in a comet's tail millions of miles long, it might fill no more than a small swimming pool. Think about that for a moment. We look up and see what appears to be a solid, bright object with a magnificent tail, but in reality we're looking at something that's mostly empty space, a gossamer veil of ancient material spread impossibly thin. It's like seeing a ghost made of starlight and time, a phantom from the deep past making itself visible through the simple act of warming up. The entire spectacle is an illusion of sorts, a trick of light and perspective that transforms a small, dark, fragile object into something that can dominate our night sky and capture our imagination. In those weeks of March and early April 2020, as Atlas brightened beyond all expectations, astronomers around the world turned their instruments toward this cosmic visitor. Professional observatories scheduled precious telescope time to study its composition through spectroscopy, analyzing the light it emitted and reflected to determine what molecules were present in its coma. Amateur astronomers set up their equipment in backyards and dark sky sites, capturing images that showed the comet's growing coma and the first hints of its developing tail. There was a sense of anticipation, a collective holding of breath as we waited to see what Atlas would become. But the universe, as it so often does, had other plans. Around April 2nd, 2020, the first signs of trouble appeared. Images of Atlas began to show that its nucleus was elongating, stretching out in a way that suggested something profound was happening. The comet's brightness, which had been increasing so dramatically, began to level off and then decline. More detailed observations confirmed what astronomers feared. ATLAS was fragmenting, breaking apart under the stresses of its approach to the sun. This dissolution wasn't violent or sudden. There was no explosion, no dramatic shattering like glass hitting stone. Instead, Atlas began to come apart gently, almost peacefully, like a sugar cube slowly dissolving in warm water. The Hubble Space Telescope, turning its unblinking eye toward the comet, captured images showing the nucleus had fragmented into at least 30 pieces, each surrounded by its own small coma of gas and dust. These fragments, some no larger than a house, continued along the comet's orbital path like a funeral procession, each piece following the same trajectory but slowly drifting apart from its siblings. Why did Atlas fragment? The truth is, we don't know for certain, and perhaps that uncertainty is part of the beauty of this story. Comets are fragile things, held together by weak forces in the cold depths of space. As they approach the sun, they experience stresses they haven't felt in thousands or millions of years. The solar heating is uneven, causing some parts to sublimate faster than others. Jets of gas erupting from the nucleus can act like tiny rocket engines, causing the comet to spin faster. Tidal forces from the sun's gravity pull harder on the side facing the sun than the side facing away. Any or all of these forces might have been enough to tear Atlas apart. There's something profoundly humbling about watching a mountain-sized object that had survived for billions of years dissolve over the course of a few weeks. Atlas had likely made many previous passages through the inner solar system, each time losing some of its material but surviving to continue its orbit. But this time, perhaps weakened by countless previous passages, perhaps simply reaching the natural end of its existence, it could no longer hold itself together. The comet that had travelled so far, that had brightened our spring skies with such promise, was returning to the dust and gas from which it had formed so long ago. Yet even in its dissolution, Atlas continued to tell us stories. The spectroscopic analysis of the fragments revealed the comet's composition in unprecedented detail. Scientists detected various carbon-bearing molecules, including C2 and CN, which gave the comet its greenish colour. They found evidence of water ice, of course, but also more exotic compounds that spoke to the conditions in the early solar system. Each molecule detected was like a word in an ancient manuscript, telling us about the time when our sun was young and the planets were still forming. The fragments of Atlas continued their journey toward perihelion, their closest approach to the sun, which occurred on May 31st, 2020. By then, the comet had faded far below naked eye visibility, observable only through telescopes as a diffuse cloud of debris. What might have been a spectacular sight in our night sky had become something more subtle, more contemplative. Instead of a brilliant cosmic display, we were witnesses to a gentle cosmic death, a quiet return to the fundamental particles from which everything in our solar system, including Earth and everyone on it, was ultimately made. But here's where our contemplation takes an interesting turn. Was Atlas, in some metaphorical sense, watching us during its approach? The question might seem absurd at first. A comet has no eyes, no consciousness, no awareness in any sense that we understand. It's a collection of ice and rock following the laws of physics, no more capable of observation than a falling stone or a drifting cloud. And yet, there's something about the way Atlas appeared, brightened, and then faded that feels almost like an encounter, a brief moment of mutual acknowledgement between Earth and cosmos. Consider that Atlas, in its journey from the Oort cloud, carried with it information about conditions in the outer solar system. The very atoms and molecules that composed its nucleus were witnesses to the formation of our solar system. In the patterns of its fragmentation, in the spectrum of light it emitted, in the trajectory of its orbit, Atlas was telling us stories about places and times we can never directly observe. In this sense, perhaps it was watching us. Or rather, it was a messenger carrying observations from the deep past and the far reaches of our cosmic neighbourhood. The timing of Atlas's appearance adds another layer to our contemplation. It arrived and fragmented during a period when humanity was experiencing its own form of fragmentation and stress. While we were focused on earthly concerns, this ancient visitor was performing its final act above our heads, largely unnoticed by a distracted world. There's a poetic symmetry in this, a reminder that the cosmos continues its ancient rhythms regardless of human affairs. The universe doesn't pause for our crises or celebrations. It simply continues, patient and eternal, following laws that existed long before Earth formed and will persist long after it's gone. When we talk about Atlas watching our planet, perhaps what we're really talking about is the way celestial events like comets serve as mirrors for human consciousness. We see in them what we bring to the observation. Ancient peoples saw omens and messages from the gods. Medieval observers saw signs of plague or war. Modern scientists see opportunities to understand the solar system's formation. But maybe, in our technological age, we can see something else. A reminder of our cosmic heritage, a connection to the vast cycles of creation and destruction that govern the universe. The fragments of Atlas continued past the Sun and began their long journey back toward the outer solar system, though whether any substantial pieces survived the passage is uncertain. If fragments did survive, they're now climbing back up the gravity well, slowing with each passing day, destined to reach aphelion, their farthest point from the Sun, sometime in the distant future. But they'll never return as Atlas. That particular configuration of ice and dust, that specific comet with its unique characteristics, is gone forever. What remains are the atoms and molecules that composed it, now dispersed through the inner solar system, some perhaps eventually falling to Earth as microscopic particles, becoming part of our world in the most literal sense. This brings us to a profound realization. Every day, Earth is bombarded by microscopic particles from space, many of them debris from comets like ATLAS. Scientists estimate that about 100 tons of extraterrestrial material falls to Earth daily, most of it in the form of dust particles so small they drift down through the atmosphere without burning up. When you walk outside on any given day, you're walking through a gentle rain of cosmic debris, invisible and imperceptible but absolutely real. Some of those particles might be from Atlas or its parent body, fragments of that ancient ice mountain that watched our planet, if only briefly, before dissolving into the cosmic background. The story of Atlas also connects to a larger narrative about the role of comets in Earth's history. there's compelling evidence that much of Earth's water arrived via cometary impacts early in our planet's history. The ratio of deuterium to hydrogen in Earth's oceans matches that found in certain types of comets, suggesting that these cosmic wanderers didn't just watch our planet, but helped create it as we know it. Every glass of water you drink, every drop of rain that falls might contain molecules that once travelled through space in the nucleus of a comet. We are, in a very real sense, made of comet stuff. As we continue our contemplation of Atlas and its journey, we might wonder about the other comets currently falling toward the Sun from the Oort cloud. At any given moment, there are likely hundreds or thousands of long-period comets somewhere in their vast orbits, most too faint to detect until they approach the inner solar system. Each one is a potential ATLAS, carrying its own cargo of ancient material, following its own precise mathematical path through space. Some will survive their solar passages and return to the outer darkness. Others, like ATLAS, will fragment and dissolve, their material recycled into the cosmic ecosystem. The Oort cloud itself, that hypothetical sphere of icy bodies surrounding our solar system, remains one of the great mysteries of astronomy. We've never directly observed it. Its existence is inferred from the orbits of long-period comets like ATLAS. According to current theories, it contains trillions of comet nuclei, a vast reservoir of primordial material left over from the solar system's formation. These objects orbit so far from the Sun that they're barely bound to our solar system at all. A passing star or the gravitational tide of the galaxy itself can disturb their orbits, sending them falling toward the Sun on journeys that take millions of years. Imagine the Oort cloud as a vast spherical library, each comet a book containing information about the early solar system. Most of these books will never be read, circling forever in the cold darkness, but occasionally one falls toward the inner solar system, where we can observe it, study it, learn from it. Atlas was one of these books, and even though it dissolved before we could read it completely, we learned valuable things from the chapters we did observe. Its chemical composition, its orbital characteristics, its fragmentation pattern, all these things add to our understanding of comets and, by extension, our understanding of our cosmic origins. The way Atlas fragmented tells us something important about the nature of cometary nuclei. They're not solid, monolithic objects, but rather loose aggregations of smaller pieces held together by weak forces. This structure, sometimes called a rubble pile, means that comets are even more fragile than we might imagine. They're like cosmic dust bunnies, accumulations of material that collected in the cold depths of space billions of years ago, and have remained largely unchanged since then. When we observe a comet, we're looking at matter in one of its most primitive forms, unchanged since the dawn of the solar system. This fragility adds poignancy to our question about whether Atlas was watching our planet. If we anthropomorphize just a little, we might imagine Atlas as an ancient, fragile observer, making one last journey to see how the inner solar system had changed since its last visit. Finding Earth transformed, covered with lights visible from space, surrounded by satellites, watched by telescopes that could detect its approach from millions of miles away, and then, perhaps overwhelmed by what it saw, or simply reaching the natural end of its existence, it gently dissolved, leaving only memories and molecules behind. But let's pull back from anthropomorphism and consider what it means for us to observe events like the fragmentation of Atlas. We are the universe's way of observing itself, conscious matter capable of contemplating its own origins. When we watch a comet dissolve, we're watching a process that has been happening for billions of years, but only in the last few centuries have there been conscious observers capable of understanding what they're seeing. In this sense, Atlas wasn't watching us, but through us, the universe was watching Atlas, bearing witness to its final transformation. The scientific instruments that observed Atlas represent humanity's extended senses, allowing us to see far beyond what our biological eyes can perceive. The ATLAS survey that discovered the comet uses sophisticated software to analyze images, comparing them to find objects that move against the background stars. The Hubble Space Telescope that captured the fragmentation can see in wavelengths invisible to human eyes, revealing details we could never observe directly. The spectrographs that analyze the comet's light can decode its chemical composition with precision that would have seemed like magic to observers just a century ago. Yet for all our technological sophistication, there's still something fundamentally mysterious about comets. We can calculate their orbits with extraordinary precision, predict their positions years in advance, analyze their composition down to trace elements. But we couldn't predict that Atlas would fragment when it did. We couldn't prevent its dissolution or preserve it for future study. We could only watch, document, and wonder. There's a humility in this, a reminder that for all our knowledge, the universe still holds surprises, still has secrets to reveal. The legacy of ATLAS extends beyond the scientific papers published about it. Every person who saw an image of the comet, everyone who read about its discovery and fragmentation, everyone who took a moment to contemplate this cosmic visitor, was touched by its passage. In an age where we're often disconnected from the night sky, focused on earthly concerns and artificial lights, comets like ATLAS remind us that we're part of something larger. They reconnect us, however briefly, to the cosmos from which we emerged. Children who learned about Atlas in 2020 might grow up to become the astronomers who observe the next great comet. Amateur astronomers who photographed ATLAS contributed to our scientific understanding of its behavior. Science communicators who explained ATLAS to the public helped maintain humanity's connection to the cosmos. Each person who looked up at the night sky, hoping to catch a glimpse of Atlas even if they couldn't see it, participated in the ancient human tradition of sky watching. In this way, Atlas created a network of observers, a temporary community united by curiosity about a cosmic visitor. The question of whether Atlas was watching our planet becomes less important than the fact that we were watching Atlas. In our observation, in our curiosity, in our attempt to understand this cosmic visitor, we demonstrated something unique about human consciousness. We're perhaps the only species on Earth capable of knowing that comets exist, of understanding their nature, of feeling wonder at their appearance. When we watch comets, we're exercising a capacity that took billions of years of evolution to develop, the ability to contemplate our place in the universe. As the fragments of Atlas continue their journey through the solar system, some falling back toward the Oort cloud, others perhaps destined to escape the solar system entirely, they carry with them the atoms that once formed a coherent structure we called a comet. These atoms, forged in the nuclear furnaces of dying stars billions of years ago, assembled in the cold of the early solar system, travelled for millennia through space, briefly warmed by our sun, and then dispersed again. It's a cycle that has been repeating since the universe began. Matter constantly being recycled, reformed, reimagined in new configurations. Somewhere in space right now, perhaps in the Oort cloud, perhaps in the Kuiper belt, perhaps in interstellar space itself, there are chunks of ice and rock that will one day become the next generation of comets. They're waiting, patient and cold, for the gravitational nudge that will send them falling toward the sun. When they arrive, decades or centuries or millennia from now, they'll find an Earth that has changed, a humanity that has evolved, technologies we can't imagine. But the fundamental experience will be the same. Conscious beings observing a cosmic visitor, wondering about its nature, its origins, its meaning. The story of Atlas reminds us that we live in a dynamic universe, where change is the only constant. Mountains erode, continents drift, species evolve and go extinct, stars are born and die, and comets fragment and dissolve. Yet within this constant change, there are patterns, cycles, and connections that bind everything together. The water in our bodies connects us to ancient comets. The carbon in our DNA connects us to dying stars. The calcium in our bones connects us to supernovae that exploded before our solar system formed. We are not separate from the cosmos, but part of it, temporary arrangements of matter and energy that have briefly achieved the ability to contemplate our own existence. As we think about Atlas and its journey, we might consider our own trajectory through space and time. Earth itself is a kind of cosmic traveller, orbiting the Sun, which orbits the centre of the Milky Way, which moves through intergalactic space. We're all on a journey through the cosmos, following paths determined by gravity and momentum, just like Atlas. The difference is that we're aware of our journey, capable of measuring it, understanding it, finding meaning in it. This awareness is perhaps the most remarkable thing in the known universe, more remarkable even than the comet that sparked this contemplation. The night sky continues its eternal rotation, stars rising and setting, planets wandering through the constellations, occasional meteors streaking across the darkness. Somewhere among those points of light, the fragments of Atlas continue their journey, invisible now but still real, still following the laws of physics that govern all matter, and somewhere else, another comet is beginning its long fall toward the Sun, carrying its own cargo of ancient material, ready to tell its own story to anyone willing to watch and listen. In the end, the question of whether Atlas was watching our planet transforms into a different question entirely. Not whether a comet can watch, but what it means for us to be watched by the cosmos itself. Every atom in the universe is connected to every other atom through the fundamental forces of nature. Every event, no matter how small or distant, affects everything else in ways we're only beginning to understand. In this interconnected cosmos, observation isn't a one-way process. When we observe the universe observes us back, not through consciousness, but through the simple fact of interaction, of photons exchanged, of gravitational influences felt, of matter and energy in constant dialogue. Atlas may be gone, but its passage through our skies left ripples that continue to propagate. The scientific data collected will inform future comet studies. The images captured will inspire future astronomers. The questions raised will motivate future research. And perhaps most importantly, the wonder it inspired, however briefly, reminded us that we live in a universe full of mystery and beauty. A cosmos that still has the capacity to surprise us, to humble us, to fill us with awe. As we contemplate the journey of Atlas, from its origin in the Oort cloud to its dissolution near the Sun, we're really contemplating the journey of matter itself through space and time. Every atom that composed Atlas had its own history stretching back to the Big Bang. Those atoms came together to form a comet, travelled through space for eons, briefly became visible to conscious observers on a small blue planet, and then dispersed again to continue their eternal journey. It's a story that encompasses the entire history of the universe, compressed into the brief life and death of a single comet. The fragments of Atlas that survived its perihelion passage are now climbing back up the Sun's gravity well, slowing with each passing moment, eventually to reach a point where they'll pause, turn, and begin falling back toward the Sun again. But that return, if it happens, won't occur for thousands of years. By then, human civilization will have changed beyond recognition. The telescopes that observed ATLAS will be museum pieces or archaeological artifacts. The astronomers who studied it will be long gone, their work preserved only in digital archives and scientific papers. But the cosmos will continue its patient cycles, indifferent to human timescales, following rhythms that transcend our brief existence. Perhaps this is the ultimate lesson of Atlas, that we are temporary witnesses to eternal processes. The cosmos doesn't need us to observe it, to understand it, to find meaning in it. It simply is, vast and patient and beautiful in its mathematical precision. But for this brief moment in cosmic history, we are here, conscious and curious, capable of watching comets dissolve and wondering what it all means. That capacity for wonder, more than any technology or scientific knowledge, is what connects us to the cosmos and to each other. As you drift towards sleep, perhaps you can imagine yourself as a passenger on Spaceship Earth, travelling through the cosmos just as Atlas travelled through the solar system. We're all following our ordained paths through space and time, influenced by forces beyond our control, yet capable of observing, understanding, and finding beauty in the journey. The same laws that governed ATLAS govern us. The same atoms that composed ATLAS compose us. We are not separate from the cosmic story, but part of it. Conscious matter contemplating itself, the universe observing its own reflection. The story of Atlas is also a reminder of the importance of paying attention. How many comets have passed through our skies unnoticed? How many cosmic events have occurred while humanity was looking elsewhere? Atlas almost became a great comet, almost provided a spectacular show for Earth's inhabitants. Instead, it gave us something perhaps more valuable, a lesson in cosmic impermanence, a reminder of the fragility of celestial bodies, and an opportunity to practice our observational skills and test our understanding of cometary physics. In the broader context of human history, the appearance and disappearance of Atlas was barely a footnote, a minor event that affected few lives directly. But in the context of our growing understanding of the cosmos, every comet we observe adds another piece to the vast puzzle of solar system formation and evolution. Atlas contributed its piece, even in dissolution, perhaps especially in dissolution, showing us how comets die, how they return their material to the cosmic ecosystem, how they participate in the endless cycle of creation and destruction that characterizes our universe. The water molecules that sublimated from Atlas as it approached the Sun didn't disappear. They're still out there, some perhaps captured by the solar wind and blown to the outer solar system, others possibly trapped in the gravitational wells of planets. A few maybe even finding their way to Earth as part of the constant rain of cosmic debris. These molecules, which once were part of a comet, might one day become part of Earth's hydrological cycle, falling as rain, flowing in rivers, perhaps even becoming part of living organisms. The journey of a water molecule from comet to cloud to creature is one of the most poetic aspects of cosmic evolution. Similarly, the dust particles released by ATLAS continue their own journeys. Some will spiral into the Sun, adding their mass to our star. Others will be captured by planets, adding imperceptibly to their growth. Still others will drift through the solar system for millions of years, occasionally colliding with other particles, slowly aggregating into larger bodies, perhaps eventually becoming part of new comets or asteroids. The material of Atlas hasn't been destroyed. It's been transformed, recycled, given new opportunities to participate in the cosmic dance. This process of recycling and transformation is fundamental to the universe. Nothing is ever truly destroyed, only changed in form. The energy that held Atlas together has been converted to heat and light and motion. The information contained in its structure has been dispersed but not erased. In a sense, Atlas still exists, just not in the form we recognized as a comet. Its existence has been distributed across space and time, its influence spreading like ripples on a cosmic pond. When we ask whether Atlas was watching our planet, we're really asking about the nature of observation itself. Does observation require consciousness? Or is there a more fundamental level at which all matter observes all other matter through the constant exchange of forces and particles? Every photon that bounced off Earth and struck Atlas was a form of observation. Every gravitational interaction between Earth and Atlas was a mutual observation. In the quantum mechanical sense, observation doesn't require consciousness, it only requires interaction. By this definition, Atlas was indeed watching our planet just as our planet was watching Atlas. But there's something unsatisfying about reducing observation to mere physical interaction. When we talk about watching, we usually mean something more: attention, interest, perhaps even intention. These are qualities we associate with consciousness, with minds capable of processing information and finding meaning in it. Atlas had none of these qualities. It was a collection of ice and rock following the laws of physics, no more conscious than a falling stone or a melting ice cube. Yet in its journey, in its brightening and dissolution, it created opportunities for conscious observation, for human minds to contemplate cosmic processes and find meaning in them. Perhaps this is the real significance of Atlas. Not that it was watching us, but that it allowed us to watch ourselves through the mirror of cosmic events. When we observe a comet, we're really observing our own relationship with the universe. We see our smallness in the vast scales of space and time. We see our connection to cosmic processes through the shared matter that composes both comets and ourselves. We see our uniqueness as conscious observers capable of understanding and appreciating these connections. The comet becomes a catalyst for self-reflection, a cosmic Rorschach test revealing our hopes, fears, and wonder. The timing of Atlas's appearance, during a period of global uncertainty and isolation, adds another layer of meaning to its story. While humanity was grappling with its own fragility, a cosmic visitor was demonstrating the universal nature of fragility. While we were forced to maintain physical distance from each other, we were reminded of our cosmic connections, the shared heritage that unites all matter in the universe. While we were focused on the microscopic world of viruses, a mountain-sized object was dissolving in the macroscopic theatre of the solar system. The juxtaposition is both humbling and oddly comforting. As we near the end of our contemplation of Atlas as a single entity, before we expand our view to consider the broader context of comets and their role in the solar system, it's worth taking a moment to appreciate the sheer improbability of our observation of this cosmic event. For Atlas to be discovered, countless conditions had to align perfectly. The ATLAS survey had to be operational, its telescopes pointed at the right part of the ski at the right time. The comet had to be bright enough to detect but not so bright as to saturate the sensors. The weather had to cooperate, providing clear skies for observation. The software had to correctly identify the moving object against the stellar background. And perhaps most importantly, there had to be humans curious enough to build these systems, to search for these objects, to care about distant chunks of ice and rock. This chain of requirements extends backward through time. For humans to observe Atlas, we first had to evolve consciousness, develop astronomy, invent telescopes, discover the nature of comets, build complex technological systems, and maintain a civilization stable enough to support scientific research. Each of these developments was itself improbable, contingent on countless other factors. The observation of Atlas represents the culmination of billions of years of cosmic and biological evolution, a moment when the universe achieved the ability to observe and understand itself through conscious beings. Yet for all this improbability, comets like ATLAS have been visiting the inner solar system for billions of years, long before there were eyes to see them or minds to contemplate them. They've been following their orbits, brightening and fading, fragmenting and dissolving, participating in the cosmic dance without any need for observation or understanding. The universe doesn't require consciousness to function. It simply is, following its laws with mathematical precision, indifferent to whether anyone is watching. But now, in this cosmic moment, we are watching. We've developed the tools and knowledge to observe comets, to understand their nature, to appreciate their beauty and significance. We've become the universe's way of appreciating itself, conscious matter capable of finding wonder in the dance of unconscious matter. When we observe Atlas or any other cosmic phenomenon, we're fulfilling a potential that has existed since the Big Bang, the potential for matter to become aware of itself, to observe its own behavior, to find meaning in its own existence. The story of ATLAS also illustrates the collaborative nature of modern astronomy. No single person discovered or studied ATLAS. It was a collective effort involving hundreds or thousands of people. The engineers who built the telescopes, the programmers who wrote the software, the astronomers who analysed the data, the support staff who maintained the facilities, the educators who trained the scientists, the taxpayers who funded the research. Each person played a role, however small, in humanity's observation of this cosmic visitor. In this sense, Atlas was watched not by individuals but by human civilization as a whole. This collaborative observation extends beyond professional scientists. Amateur astronomers around the world contributed observations of ATLAS, tracking its brightness, capturing images, sharing their data with a global community. Science communicators translated complex astronomical concepts into accessible language, helping the public understand and appreciate what was happening. Artists created visualizations and interpretations of ATLAS, adding aesthetic and emotional dimensions to the scientific observations. Each contribution added to our collective understanding and appreciation of this cosmic event. The digital age has transformed how we observe and share cosmic events. Images of ATLAS were distributed globally within seconds of being captured. Scientific papers about the comet were published online, accessible to anyone with an internet connection. Social media allowed people to share their excitement and wonder in real time. Virtual communities formed around the observation of ATLAS, connecting people across continents and cultures through their shared interest in a distant comet. In a sense, humanity created a global sensory network focused on this single cosmic object, a collective eye watching Atlas as it approached and dissolved. But even with all our technology and collective effort, we could only observe Atlas from a distance. We couldn't send a spacecraft to study it up close, couldn't sample its material directly, couldn't prevent its fragmentation. We were limited to passive observation, watching from afar as cosmic processes played out beyond our control. There's both frustration and beauty in this limitation, a reminder that for all our technological prowess, we're still bound to a single planet, still limited in our ability to explore and understand the cosmos directly. The story of Atlas raises questions about all the comets we don't observe. How many cosmic visitors pass through the solar system undetected? How many fragment and dissolve without any witness? The universe is vast, and our observational capabilities, while impressive, cover only a tiny fraction of the sky at any given moment. For every Atlas we discover, there might be dozens or hundreds of similar objects that pass by unnoticed. The cosmic show continues whether we're watching or not. This realization can be either depressing or liberating, depending on your perspective. On one hand, we're missing most of the cosmic action, limited by our technology and the sheer scale of the universe. On the other hand, there's something beautiful about a universe that doesn't perform for an audience, that simply exists and evolves according to its own logic. The cosmos doesn't need our observation to be magnificent. It simply is magnificent, and we're privileged to observe whatever small fraction of its magnificence we can perceive. As we prepare to expand our contemplation beyond Atlas to consider the broader phenomenon of comets and their role in the solar system's history, it's worth reflecting on what this single comet has taught us. Through ATLAS, we've seen the fragility of cosmic bodies, the power of solar heating, the importance of patient observation, the value of international scientific collaboration, and the deep connections between cosmic events and human consciousness. We've been reminded that we live in a dynamic universe where change is constant and surprise is always possible. Atlas also demonstrated the importance of being prepared for the unexpected. Astronomers had models predicting how bright the comet would become, but reality diverged from these predictions. The comet brightened faster than expected, then fragmented earlier than anticipated. These surprises weren't failures of science, but opportunities to refine our understanding, to improve our models, to learn something new about cometary behavior. Every surprise in science is a gift, a chance to discover something we didn't know. The fragmentation of ATLAS provided a particularly valuable scientific opportunity. While we've observed other comets fragment, Each event is unique, providing new insights into cometary structure and composition. The Hubble Space Telescope's images of Atlas breaking apart will be studied for years, compared with observations of other fragmenting comets, used to test and refine theories about how these cosmic icebergs hold together and come apart. Even in death, Atlas contributed to human knowledge. There's a certain poetry in the fact that Atlas was discovered by a system designed to protect Earth from asteroid impacts. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, searches for near-Earth objects that might pose a threat to our planet. In the process of looking for danger, it found beauty. While searching for objects that might end civilization, it discovered an object that enriched our understanding of the cosmos. This dual nature of astronomical observation, simultaneously practical and philosophical, protective and contemplative, reflects the complex relationship between humanity and the cosmos. The name Atlas itself carries mythological weight. In Greek mythology, Atlas was a titan condemned to hold up the sky for eternity. The comet ATLAS, in its brief appearance, seemed to carry the weight of cosmic history, bringing messages from the early solar system to our modern world. And like the mythological Atlas, the comet bore its burden until it could bear it no more, finally releasing its hold and dissolving into the cosmic background. The parallel between myth and reality adds another layer of meaning to our contemplation. As we watch the night sky, knowing that the fragments of Atlas are out there somewhere, too faint to see but still real, we might wonder about the future of cometary observation. What new technologies will we develop to study these cosmic visitors? Will we one day be able to send spacecraft to rendezvous with incoming comets, to study them up close before they fragment? Will we develop the ability to predict fragmentation events, to understand why some comets survive their solar passages while others dissolve? The future of cometary science is as open and full of possibility as the cosmos itself. But perhaps the most important legacy of Atlas isn't scientific but philosophical. This comet reminded us that we're part of a larger story, a cosmic narrative that began billions of years before we existed and will continue billions of years after we're gone. We're temporary participants in an eternal process, brief witnesses to cosmic events that connect us to the deepest history of the universe. When we observe a comet like ATLAS, we're not just watching a chunk of ice and rock. We're observing our own origins, our own future, our own place in the vast tapestry of existence. The question, was Atlas watching our planet, ultimately becomes less important than the fact that we asked it. The ability to pose such questions, to wonder about the nature of observation and consciousness, to find meaning in cosmic events, is what makes us unique in the known universe. We are matter that has become conscious, able to contemplate its own existence, and find wonder in the cosmos from which it emerged. When we watch comets, we're exercising the universe's capacity for self-observation, fulfilling a potential that has existed since the first moments after the Big Bang. As we transition from contemplating Atlas as an individual comet to considering the broader phenomenon of comets throughout the solar system's history, we carry with us the lessons of this single cosmic visitor. Atlas taught us about fragility and impermanence, about the importance of observation and the limits of prediction, about the connections between cosmic events and human consciousness. These lessons will inform our broader contemplation, helping us understand not just what comets are, but what they mean for our understanding of ourselves and our place in the universe. The journey of Atlas from the Oort cloud to dissolution near the Sun is complete, but our journey of understanding has just begun. As we drift deeper into contemplation of cosmic phenomena, we'll explore the vast reservoir of comets waiting in the darkness, the role these cosmic messengers have played in Earth's history, and the intricate orbital dances that govern their movements. But always, underlying these explorations, will be the memory of Atlas, that fragile mountain of ice that briefly brightened our skies, before returning to the dust from which it came. In the silence of space, where Atlas once travelled, its atoms now drift on separate paths, some falling sunward, others climbing back toward the outer darkness. Each atom carries with it the history of a comet, the memory of a structure that held together for billions of years before dissolving in a cosmic instant. These atoms will eventually become part of new structures, perhaps new comets, perhaps planets, perhaps even living beings. The story of ATLAS ends, but the story of its constituent matter continues, eternal and ever-changing, like the universe itself. The dissolution of Atlas near the Sun was not an ending but a transformation, a return to the cosmic reservoir from which all comets emerge. To truly understand what Atlas was and what its journey meant, we need to travel backward in time and outward in space, to the very edge of our solar system and beyond. There, in the perpetual darkness, lies one of astronomy's most elegant theories and mysterious realities. The Oort cloud, a vast spherical shell of icy bodies that surrounds our solar system, like a cosmic snow globe, holding within its frozen embrace the raw materials from which comets, like ATLAS, are born. Picture, if you will, the solar system as most people understand it. At the centre burns our sun, that familiar yellow star that has warmed Earth for billions of years. Orbiting around it are the 8 planets we learned about in school. Mercury hugging close to the solar furnace, Venus shrouded in clouds, our blue Earth with its single large moon, rusty Mars with its polar caps, and then the 4 giants, Jupiter with its storms, Saturn with its rings, Uranus tilted on its side, and distant Neptune with its deep blue atmosphere. Beyond Neptune lies the Kuiper Belt, that disk of icy bodies that includes Pluto and countless other frozen worlds. But even this vast expanse, stretching out to about 50 astronomical units from the Sun, is just the beginning. The true boundary of our solar system lies much, much farther out, in a realm so distant and dark that it exists more in mathematical models than in direct observation. The Oort cloud begins where the Kuiper Belt ends, but while the Kuiper Belt is a relatively flat disk aligned with the plane of the planets, the Oort cloud is a sphere, encompassing our entire solar system in all directions. Its inner edge is thought to be about 2,000 astronomical units from the Sun, which means light from our star takes more than 11 days to reach it. But that's just the beginning. The Oort cloud extends outward to perhaps 100,000 astronomical units, nearly 2 light-years from the Sun. At that distance, our Sun would appear as just another star in the sky, barely distinguishable from the cosmic background. The gravitational grip of our star at that distance is so weak that the slightest perturbation, a passing star, the gravitational tide of the galaxy itself, can send objects tumbling inward toward the Sun or outward into interstellar space. Within this vast sphere, astronomers estimate there are trillions of icy bodies, ranging in size from tiny pebbles to mountains larger than any on Earth. The total mass of the Oort cloud is uncertain, but it might be several times the mass of Earth, spread out over a volume so vast that if you were floating in the Oort cloud, you might not be able to see the nearest cometary nucleus with the naked eye. It's a place of almost incomprehensible emptiness, where the average distance between objects might be comparable to the distance between Earth and the Sun. Yet despite this emptiness, or perhaps because of it, the Oort cloud is one of the most important structures in our solar system, a cosmic reservoir that has been feeding comets into the inner solar system for billions of years. The existence of the Oort cloud was first proposed by Dutch astronomer Jan Oort in 1950, though Estonian astronomer Ernst Üppig had suggested something similar in 1932. Oort was trying to solve a puzzle that had bothered astronomers for decades. Why do we still see long-period comets? Comets lose material every time they pass close to the Sun. After a few hundred passages, most comets should be completely depleted, reduced to dark, dead nuclei, or dissolved entirely. Yet we continue to observe fresh comets, objects that appear to be making their first or second passage through the inner solar system. Where do these pristine comets come from? Oort's solution was elegant and profound. He proposed that there must be a vast reservoir of cometary nuclei far from the Sun, so far that they've remained frozen and unchanged since the formation of the solar system. Occasionally one of these nuclei is disturbed from its distant orbit and falls toward the Sun, becoming a long-period comet. This reservoir, the Oort cloud, acts like a cosmic time capsule, preserving primordial material from the birth of our solar system and occasionally releasing it for our observation. When we see a comet like ATLAS, we're seeing material that has been in deep freeze for 4.6 billion years, suddenly awakened and transformed by the sun's heat. But how did the Oort cloud form in the first place? The current theory is that the objects in the Oort cloud didn't form where they are now. Instead, they formed much closer to the Sun, in the region where the giant planets now orbit. During the early solar system, the region between Jupiter and Neptune was filled with countless small icy bodies, the building blocks that might have formed additional planets if conditions had been different. But the gravitational influence of the growing giant planets, particularly Jupiter with its immense mass, scattered these objects in all directions. Some were ejected from the solar system entirely, flung into interstellar space to wander between the stars. Others were thrown into the inner solar system, where they collided with the forming terrestrial planets, possibly delivering water and organic molecules to the young Earth. But a significant number were scattered into highly elliptical orbits that took them far from the Sun, but not quite far enough to escape entirely. Over millions of years, these scattered objects had their orbits modified by various forces. Close encounters with the giant planets continue to pump up their orbits, sending them farther from the Sun. Meanwhile, the gravitational influence of passing stars and the galaxy itself circularized their orbits at extreme distances. The end result was the Oort cloud, a roughly spherical distribution of icy bodies loosely bound to the Sun, orbiting so slowly that a single revolution might take millions of years. These objects have been out there ever since, a frozen archive of the early solar system, waiting for the gravitational nudge that will send them falling back toward the Sun. The Oort cloud is not uniform, but is thought to have two distinct regions. The outer Oort cloud, extending from about 20,000 to 100,000 astronomical units, is roughly spherical and is the source of most long-period comets. The inner Oort cloud, also called the Hills cloud after astronomer Jack Hills, who proposed its existence, extends from about 2,000 to 20,000 astronomical units and is shaped more like a thick disk. Objects in the Hills cloud are more strongly bound to the Sun and less likely to be perturbed into the inner solar system, but they act as a reservoir that can replenish the outer Oort cloud as objects are lost to interstellar space or sent sunward as comets. Living in the Oort cloud, if we can call it living, must be an existence of profound stillness and cold. The temperature out there is only a few degrees above absolute zero, cold enough that even substances we think of as gases on Earth exist as solid ices. Water ice, of course, but also frozen methane, ammonia, carbon dioxide, and even more exotic compounds. These ices are mixed with dust and rock in proportions that vary from object to object, creating a diverse population of frozen worlds. Some might be mostly ice with a small rocky core. Others might be more like dirty snowballs with ice and rock mixed throughout. Still others might have differentiated structures with distinct layers of different compositions. The orbital speeds in the Oort cloud are almost impossibly slow by inner solar system standards. While Earth orbits the Sun at about 30 kilometers per second, an object in the outer Oort cloud might be moving at only a few meters per second relative to the Sun. At that speed, it would take you several hours to walk the distance the object travels in a second. These slow speeds mean that collisions between objects when they occur are gentle, more like a cosmic kiss than a violent impact. Objects might stick together when they collide, gradually building up larger bodies, or they might simply bounce off each other and continue on their separate ways. The darkness in the Oort cloud is absolute in a way that's difficult for Earth dwellers to comprehend. The sun at that distance provides less light than the full moon does to Earth. The stars would be visible, of course, brilliant and unwinking in the absence of any atmosphere, but they would provide no meaningful illumination. An object in the Oort cloud exists in perpetual night. Its surface features invisible even to itself, shaped by processes that occur over billions of years in complete darkness. There are no days or nights, no seasons, no weather in any sense we understand. Just the slow wheel of the stars as the object makes its million-year orbit around a sun too distant to warm even the darkest rock. Yet this frozen, dark realm is not static. The Oort cloud is constantly evolving, shaped by forces both internal and external. Within the cloud, the collective gravity of all the objects creates a complex, ever-changing gravitational field. Objects perturb each other's orbits, sometimes sending a neighbour tumbling toward the sun, sometimes capturing passing objects into temporary binary systems. The cloud as a whole responds to the gravitational tide of the galaxy, compressed and stretched as the solar system orbits the galactic centre. When the solar system passes through the galactic plane, the increased stellar density can trigger comet showers, sending multiple objects toward the inner solar system simultaneously. Perhaps the most dramatic influences on the Oort cloud come from stellar encounters. Although space is vast and stars are far apart over billions of years, other stars occasionally pass close enough to the solar system to gravitationally disturb the Oort cloud. A star passing within a light-year of the Sun, which happens perhaps every 100,000 years, can send millions of comets into new orbits. Some will be ejected from the solar system, their multi-million-year connection to our Sun finally severed. Others will be sent plunging toward the inner solar system, beginning journeys that will take them close to the Sun for the first time since their formation. Atlas might have begun its final journey during such an encounter, nudged from its stable orbit by the gravity of a passing star hundreds of thousands of years ago. The star Gliese 710 is currently approaching our solar system and is predicted to pass within about 0.16 light-years of the Sun in approximately 1.3 million years. When it does, it will pass directly through the outer Oort cloud, potentially triggering a comet shower that could last for millions of years. This future event gives us a glimpse into the dynamic processes that have been shaping the Oort cloud throughout the solar system's history. Every close stellar encounter leaves its mark on the cloud, rearranging orbits, creating and destroying structures, ensuring that the Oort cloud is never truly stable but always evolving. The Oort cloud also exchanges material with interstellar space. Just as our solar system can capture objects from other stars, we undoubtedly lose objects to space as well. Some astronomers estimate that the solar system might capture 1 or 2 interstellar objects per century, temporarily adding them to the Oort cloud population. Similarly, objects ejected from our Oort cloud become interstellar travelers, carrying information about our solar system to the cosmos. In this way, the Oort cloud is not a closed system, but part of a galactic ecosystem, exchanging material with other star systems in a slow, cosmic commerce that has been occurring since the galaxy formed. Recent discoveries have given us new insights into the nature of the Oort cloud and its relationship to comets. The detection of objects like Oumuamua and Borisov, the first confirmed interstellar objects to pass through our solar system, has shown us that the galaxy is full of wandering bodies ejected from their home systems and travelling between the stars. Some of these objects might be captured by our Sun's gravity and become part of the Oort cloud, adding exotic material from alien solar systems to our cosmic reservoir. When we observe a comet, we might be seeing not just material from our own solar system's formation, but possibly material from other stars, other planetary systems, other histories entirely. The composition of Oort cloud objects tells us about conditions in the early solar system. spectroscopic observations of comets, which we believe originate in the Oort cloud, reveal a rich chemistry of organic molecules. We've detected amino acids, the building blocks of proteins, in cometary material. We've found complex carbon chains that might have served as precursors to life. The presence of these molecules suggests that the building blocks of life are not unique to Earth, but are common throughout the solar system, preserved in the frozen archives of the Oort cloud and delivered to planets by cometary impacts. This brings us to one of the most profound questions about the Oort cloud and comets, their role in the origin of life on Earth. The early Earth was a hellish place, bombarded by asteroids and comets during a period called the Late Heavy Bombardment, about 3.9 billion years ago. This bombardment, which might have been triggered by a rearrangement of the giant planet's orbits, would have delivered vast amounts of water and organic molecules to Earth's surface. Some scientists estimate that a significant fraction of Earth's water came from cometary impacts during this period. If this is true, then every glass of water you drink contains molecules that once resided in the Oort cloud, that travelled for millions of years through space before splashing down on our young planet. But water wasn't the only thing comets delivered. The organic molecules found in comets include many of the compounds necessary for life as we know it. Amino acids, nucleobases, sugars, and other complex organic molecules have all been detected in cometary material. When comets impacted the early Earth, they would have delivered these molecules to the surface, creating a rich organic soup from which life might have emerged. The energy from the impacts themselves might have driven chemical reactions, creating even more complex molecules. In this view, comets were not just passive deliverers of material, but active participants in the chemistry that led to life. The idea that life's ingredients came from space is called panspermia, and while it remains controversial, evidence continues to mount that at least the building blocks of life are common in the cosmos. Every comet that enters the inner solar system carries with it a sample of this cosmic organic chemistry, a test tube from nature's vast laboratory. When Atlas dissolved near the Sun, it released organic molecules that had been frozen for billions of years, adding its contribution to the cosmic inventory of life's building blocks. Some of these molecules might eventually find their way to Earth or other planets, continuing the process of cosmic seeding that has been occurring throughout the solar system's history. The Oort cloud might also play a role in the long-term evolution of life on Earth through its influence on impact rates. Periodic comet showers, triggered by stellar encounters or the solar system's passage through the galactic plane, might correlate with mass extinction events in Earth's history. The idea of periodic extinctions caused by comet impacts remains debated, but there's no doubt that impacts have played a major role in shaping the evolution of life. The asteroid impact that killed the dinosaurs 66 million years ago cleared the way for mammals to dominate the planet. Without that impact, humans might never have evolved. In this sense, we owe our existence partly to the cosmic bombardment that the Oort cloud helps facilitate. But the Oort cloud's influence on Earth isn't always destructive. Cometary dust, constantly raining down on Earth as comets pass through the inner solar system and shed material, adds tons of extraterrestrial material to our planet every day. This dust contains not just organic molecules, but also rare elements that might play important roles in biological processes. Some scientists have suggested that cometary dust might even influence weather patterns by providing nucleation sites for cloud formation in the upper atmosphere. The Oort cloud, through the comets it sends our way, maintains a constant, subtle connection with Earth, a cosmic drip feed of material from the outer darkness. The study of the Oort cloud also tells us about the formation and evolution of planetary systems in general. Other stars almost certainly have their own Oort clouds, their own reservoirs of cometary material left over from planetary formation. When we observe exoplanetary systems, we can infer the presence of these distant comet clouds from the behavior of dust and gas in the system. Some young stars show evidence of active comet bombardment, with spectra revealing the presence of gases typically associated with cometary activity. These observations suggest that the processes we see in our own solar system, the scattering of small bodies, the formation of distant reservoirs, the occasional cometary impact, are universal features of planetary system evolution. The Oort cloud also serves as a bridge between our solar system and interstellar space. Objects in the outer Oort cloud are so weakly bound to the Sun that they're almost interstellar objects already. A small perturbation could send them on trajectories that take them to other stars, carrying information about our solar system across the galaxy. Similarly, our Oort cloud might contain objects captured from other stars, cosmic immigrants that have made our solar system their home. In this way, the Oort cloud is not just a feature of our solar system, but part of the galactic community, participating in the slow exchange of material between stars. As we contemplate the vastness of the Oort cloud, it's worth considering what fraction of it we've actually observed. Every comet we've seen represents just one object from a population of trillions. It's like trying to understand an ocean by examining a single drop of water. Most of the Oort cloud will never be observed directly. The objects are too small, too dark, too distant to see with any telescope we can imagine building. We know the Oort cloud exists primarily through inference, through the comets it sends our way and the gravitational effects it might have on the outer planets. It's a humbling reminder of how much of the universe remains hidden from our view, knowable only through its effects on things we can see. The future of Oort cloud science is exciting and full of possibilities. New telescopes and surveys will discover more long-period comets, each one providing another sample from the cosmic reservoir. Space missions to comets will return samples to Earth, allowing us to study Oort cloud material in laboratories with instruments far more sensitive than anything we can send to space. Perhaps one day we'll even send probes to the Oort cloud itself, though such missions would take centuries or millennia to reach their destinations. The information they would send back would be received by our distant descendants, a gift from our generation to theirs, connecting us across time just as the Oort cloud connects us across space. But perhaps we don't need to wait for future technology to appreciate the wonder of the Oort cloud. Every clear night, when you look up at the stars, you're looking through the Oort cloud. It's there, invisible but present, a vast sphere of frozen worlds surrounding us in all directions. Occasionally, one of these worlds begins its long fall toward the Sun, becoming a comet that might, if we're lucky and attentive, grace our skies with its presence. Each comet is a messenger from the Oort cloud, carrying news from the edge of the solar system, reminding us that we're part of a structure far larger than the familiar planets, part of a system that extends nearly halfway to the nearest star. The relationship between Earth and the Oort cloud is not one way. While the Oort cloud sends comets our way, Earth's gravity also influences the trajectories of these cosmic visitors. Every comet that passes near Earth has its orbit altered slightly by our planet's gravity. Over billions of years, Earth and the other planets have sculpted the population of comets, selecting which ones survive and which ones are destroyed or ejected. We're not passive recipients of cometary visits, but active participants in the cosmic dance that determines which comets we see and when we see them. The history of cometary impacts on Earth is also a history of Earth's gravitational influence on comets, a mutual relationship that has been evolving since both Earth and the Oort cloud formed. Moving from the vast repository of the Oort cloud to the specific chemistry of comets, we encounter another layer of cosmic mystery. The water in comets has a story to tell, one written in the language of isotopes and molecular ratios. When scientists analyze the water from comets, they're not just looking at H2O. They're examining the ratio of heavy water to regular water, the presence of deuterium versus ordinary hydrogen, signatures that can tell us where and when this water formed. These molecular fingerprints are like cosmic DNA, encoding information about the conditions in which the water was created and preserved. The story of water in our solar system begins in the interstellar medium, that vast expanse of gas and dust between the stars. In the cold darkness of space, Water forms on the surfaces of tiny dust grains, molecule by molecule, hydrogen and oxygen atoms coming together in a slow, cosmic chemistry. This water becomes incorporated into the collapsing cloud that will eventually form a star and its planets. As the cloud collapses and heats up, some of this water is destroyed, broken apart by radiation and heat. But in the cold outer regions of the forming solar system, beyond what astronomers call the snow line, water remains frozen, incorporated into the growing bodies that will become comets and the icy moons of the outer planets. The water in comets is primordial, unchanged since those early days of solar system formation. When we measure the deuterium to hydrogen ratio in cometary water, we're measuring a property that was set 4.6 billion years ago. Different comets show different ratios, suggesting they formed at different distances from the Sun or under different conditions. Some comets have water very similar to Earth's oceans, supporting the idea that cometary impacts contributed significantly to Earth's water inventory. Others have quite different ratios, suggesting that Earth's water came from multiple sources, or that some processes altered either Earth's or the comet's water over time. But water is just the beginning of cometary chemistry. Comets are cosmic laboratories, where molecules that could never survive on Earth's surface exist in abundance. In the cold vacuum of space, molecules that would instantly react with each other on Earth can coexist peacefully for billions of years. When a comet approaches the Sun and begins to sublimate, these molecules are released, creating a complex chemistry in the coma that astronomers can observe and analyze. We've detected dozens of different molecules in comets, from simple compounds like carbon monoxide and methane, to complex organic molecules with chains of carbon atoms. One of the most intriguing discoveries in cometary chemistry is the presence of glycine, the simplest amino acid. The Stardust mission, which returned samples from Comet Wild 2 to Earth in 2006, found glycine in the collected material. This was the first direct evidence that comets contain amino acids, the building blocks of proteins. The discovery supports the idea that comets could have delivered the ingredients for life to early Earth. But glycine is just the beginning. Other amino acids, nucleobases, the letters of the genetic code, and complex organic polymers have all been detected in comets or in laboratory simulations of cometary chemistry. The organic molecules in comets aren't randomly distributed, but show patterns that tell us about their formation. Some molecules are more abundant in comets from the Oort cloud than in those from the Kuiper belt, suggesting different formation conditions or evolutionary histories. The relative abundances of different molecules can tell us about the temperature at which the comet formed, the radiation environment it experienced, and the chemical processes that have occurred during its long storage in the outer solar system. Each comet is a book written in molecular language, telling its own unique story of formation and evolution. The chemistry of comets also includes some truly exotic compounds. Comets contain molecules like hydrogen cyanide, formaldehyde, and methanol, substances that would be deadly poisons on Earth, but are essential ingredients in the cosmic chemistry that leads to life. In the coma of a comet, these molecules undergo complex photochemistry, driven by solar ultraviolet radiation. New molecules form, others break apart, and a rich chemical ecosystem develops in the space around the comet's nucleus. This chemistry is ephemeral, lasting only as long as the comet remains active, but it provides a window into chemical processes that might have occurred on early Earth, or that might be occurring on other worlds throughout the universe. The dust in comets is equally fascinating. This isn't ordinary dust like you might find under your bed, but cosmic dust, particles that formed in the outer atmospheres of dying stars or in the interstellar medium. Some cometary dust grains are literally stardust, formed billions of years ago in stellar atmospheres and preserved unchanged in the comet's nucleus. When we collect and analyze these grains, we're holding pieces of stars that died before our sun was born, material that has traveled across the galaxy before finding its way into our solar system. The mineral composition of cometary dust tells us about the conditions in the early solar system. Some grains show evidence of high-temperature processing, suggesting they formed close to the Sun and were then transported to the outer solar system where they were incorporated into comets. This radial mixing of material means that comets contain samples from across the entire solar system, a mixed collection that preserves evidence of processes that occurred at different distances from the Sun. It's like having a geological collection from an entire planet compressed into a single small body. The organic material in cometary dust is particularly complex. These aren't simple molecules, but complex polymers, chains, and networks of carbon atoms decorated with hydrogen, oxygen, nitrogen, and other elements. Some of these polymers are so complex that we haven't fully characterized them yet. They represent a form of organic chemistry that doesn't occur naturally on Earth, products of billions of years of slow chemical evolution in the cold darkness of space. When these polymers are delivered to a planet's surface and exposed to liquid water and energy sources, they might undergo further chemical evolution, potentially leading to the formation of self-replicating molecules and the origin of life. The isotopic composition of cometary material provides another window into cosmic history. Elements come in different isotopic varieties, atoms with the same number of protons but different numbers of neutrons. The ratios of these isotopes can tell us about the nuclear processes that created the elements and the physical conditions under which they were incorporated into comets. For example, the ratio of carbon-12 to carbon-13 in cometary organic matter can tell us whether the carbon came from the interstellar medium or was processed in the solar nebula. The ratio of oxygen-16 to oxygen-18 can tell us about the temperature at which water ice formed. These isotopic signatures are like fingerprints, unique identifiers that link cometary material to specific cosmic processes and environments. The noble gases trapped in cometary ice provide yet another piece of the puzzle. These chemically inert gases, helium, neon, argon, krypton, and xenon, don't form compounds, but they can be trapped in ice as it forms. The abundances and isotopic ratios of noble gases in comets can tell us about the conditions in the early solar system and the sources of volatile elements. Some comets show noble gas signatures similar to the solar wind, suggesting they incorporated material directly from the young sun. Others show signatures more similar to the interstellar medium, suggesting they preserve pre-solar material. These differences help us understand the heterogeneity of the early solar system and the diverse sources of material that went into forming comets. The role of comets in delivering volatiles to the terrestrial planets extends beyond water. Comets also contain significant amounts of carbon dioxide, methane, ammonia, and other volatile compounds that could have contributed to the atmospheres of Earth and other planets. The early Earth probably had a very different atmosphere than it does today, and cometary impacts might have played a role in establishing the chemical conditions that eventually led to the oxygen-rich atmosphere we breathe. The carbon delivered by comets became incorporated into the carbon cycle, eventually forming the coal, oil, and gas deposits that power our civilization. In a very real sense, the energy that lights our cities and powers our technology might have originated in the Oort cloud, delivered to Earth by ancient cometary impacts. But comets don't just deliver material, they also deliver energy. A large cometary impact releases enormous amounts of energy, equivalent to millions of nuclear weapons. This energy can drive chemical reactions that wouldn't otherwise occur, creating new molecules from the raw materials present at the impact site. Laboratory experiments simulating cometary impacts have produced amino acids and other organic molecules, suggesting that impacts themselves might have been crucial in the origin of life. The shock waves from impacts can also create unique mineral structures and chemical environments that might have served as catalysts for prebiotic chemistry. Every crater on Earth, the Moon, and other planets is not just a scar from a violent event, but potentially a site where cosmic chemistry advanced toward complexity and perhaps life. The study of cometary chemistry has been revolutionized by space missions that have visited comets up close. The European Space Agency's Rosetta mission which orbited comet 67P Churyumov-Gerasimenko from 2014 to 2016, provided unprecedented insights into cometary composition and behavior. Rosetta detected molecular oxygen in the comet's coma, a surprising discovery that challenged our understanding of how comets form and evolve. The mission also revealed that the comet's water had a deuterium to hydrogen ratio 3 times higher than Earth's oceans, suggesting that comets like 67P were not the primary source of Earth's water. These findings remind us that each comet is unique, and generalizations about cometary contributions to Earth must be made carefully. The Philae lander, deployed from Rosetta, made the first soft landing on a comet's surface, though its mission was shortened when it landed in shadow and couldn't recharge its solar panels. During its brief operational period, Philae detected organic molecules on the comet's surface, including compounds that had never before been detected on a comet. The lander's instruments suggested that the comet's surface was harder than expected, covered with a crust of sintered ice and dust that had been processed by billions of years of cosmic radiation. This surface processing creates a kind of armor that protects the pristine material below, preserving the comet's primordial composition until it's exposed by sublimation or impact. NASA's Deep Impact mission took a more violent approach to studying cometary composition. In 2005, it deliberately crashed an impactor into Comet Tempel 1, creating a crater and exposing fresh material from below the surface. The impact revealed that the comet's interior was much dustier than expected, with a fine, powdery consistency rather than solid ice. The mission detected water ice, of course, but also a variety of organic compounds and minerals that told a complex story of the comet's formation and evolution. The impact also showed that comets are incredibly fragile, with a tensile strength less than that of snow on Earth. This fragility explains why comets like TLAS can fragment so easily when stressed by solar heating. The Japanese Hayabusa 2 mission, while primarily focused on asteroids, has implications for our understanding of comets as well. The samples it returned from asteroid Ryugu contain organic molecules and water-bearing minerals, showing that the distinction between asteroids and comets might not be as clear-cut as once thought. Some objects might be transitional between the two categories, or might have started as comets and evolved into asteroid-like bodies after losing their volatile components. This blurring of categories reminds us that the solar system is a continuum of objects with diverse compositions and histories, not a collection of discrete types. Future missions promise to reveal even more about cometary chemistry and its implications for life. The proposed Comet Interceptor mission would wait in space for a pristine comet from the Oort cloud to approach the inner solar system, then intercept it for close study. Such a mission could provide our first look at a truly primordial comet, one making its first passage through the inner solar system. The chemical and isotopic signatures of such a comet would provide invaluable information about conditions in the early solar system and the Oort cloud. As we transition from chemistry to orbital dynamics, we begin to see how the physical paths comets take through the solar system are as important as their composition in determining their influence on planets like Earth. The orbits of comets are not random but follow precise mathematical laws, the same laws that govern the motion of planets, moons, and every other object in the cosmos. Yet within these rigid laws, there's room for incredible diversity and complexity. The orbital dance of comets is a choreography written in the language of gravity, a performance that has been playing out since the solar system began and will continue until the sun itself dies. The fundamental principle governing cometary orbits is Newton's law of universal gravitation, refined by Einstein's general relativity for extreme conditions. Every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This simple law, which can be written in a single line of mathematics, produces the incredible variety of orbits we observe, from the nearly circular orbits of the planets to the extremely elongated orbits of long-period comets, from stable resonances that repeat precisely to chaotic trajectories that are impossible to predict far into the future, all emerge from this fundamental principle. Long-period comets like ATLAS follow orbits that are extremely elongated ellipses, so stretched that they're almost parabolic. These orbits take comets from the frigid depths of the Oort cloud to the scorching vicinity of the Sun and back again, a journey that can span millions of years. The mathematical beauty of these orbits lies in their precision. Despite the vast distances and times involved, a comet will return to exactly the same point in its orbit, following a path determined by the initial conditions of its formation or last major perturbation. It's a cosmic clockwork of extraordinary accuracy, though one whose period is so long that human civilizations rise and fall between ticks. The eccentricity of a comet's orbit, a measure of how elongated it is, tells us about the comet's history and origin. Comets from the Oort cloud typically have eccentricities very close to 1, meaning their orbits are extremely elongated. Comets from the Kuiper belt have lower eccentricities, though still higher than most planets. This difference in orbital shape is one way astronomers can determine where a comet originated. The inclination of the orbit, the angle it makes with the plane of the planets, provides another clue. Oort cloud comets can approach from any direction, their orbits randomly oriented in space. Kuiper belt comets tend to have orbits more aligned with the planetary plane, though still with significant inclinations. The concept of orbital energy is crucial to understanding cometary motion. An object's orbital energy determines whether it's bound to the Sun or will escape to interstellar space. Comets in the Oort cloud have orbital energies very close to zero, meaning they're just barely bound to the solar system. A small perturbation can give them positive energy, sending them on hyperbolic trajectories that will carry them away from the Sun forever. Conversely, interactions with planets can remove energy from a comet's orbit, capturing a previously long-period comet into a shorter orbit. This process, called orbital evolution, gradually transforms the population of comets, creating families with similar orbital characteristics. The three-body problem, one of the most famous challenges in celestial mechanics, becomes relevant when considering how comets interact with planets. While the two-body problem, predicting the motion of two objects interacting gravitationally, has an exact solution, adding a third body makes the problem analytically unsolvable in most cases. We can compute numerical solutions with high precision, but there's no general formula that gives the position of all three bodies at any future time. This mathematical complexity means that cometary orbits can be chaotic, sensitive to initial conditions in ways that make long-term prediction impossible. A comet passing near Jupiter might have its orbit change dramatically, but exactly how depends on the precise geometry of the encounter, differences of meters in position potentially leading to differences of millions of kilometers in the final orbit. Orbital resonances add another layer of complexity to cometary dynamics. A resonance occurs when two orbiting bodies have periods related by a simple ratio, like 2:1 or 3:2. These resonances can stabilize or destabilize orbits, creating regions of the solar system where comets can be trapped for millions of years, or from which they're quickly ejected. The Kuiper belt, for example, has a complex structure sculpted by resonances with Neptune. Some comets are trapped in these resonances, orbiting in lockstep with a giant planet. Others are in unstable regions, slowly leaking into the inner solar system to become short-period comets. The Kozai mechanism, discovered by Japanese astronomer Yoshihide Kozai, describes how the inclination and eccentricity of an orbit can oscillate over time due to gravitational perturbations. For comets with highly inclined orbits, this mechanism can cause dramatic changes in orbital shape, sometimes bringing a comet that normally stays far from the Sun into the inner solar system. The Kozai mechanism operates on timescales of thousands to millions of years, slowly modulating cometary orbits in ways that can suddenly make a previously invisible comet become a spectacular naked-eye object. The concept of the perihelion, a comet's closest approach to the Sun, is crucial for understanding cometary behavior. It's at perihelion that comets experience maximum heating, maximum stress, and maximum activity. The perihelion distance determines whether a comet will survive its passage or fragment like Atlas. Comets with perihelia inside Mercury's orbit, called sun grazers, experience extreme conditions that often lead to complete disruption. The Kreutz family of sun grazers, all fragments of a single parent comet that broke apart centuries or millennia ago, provides a dramatic example of how orbital dynamics and physical fragmentation are interconnected. The distribution of cometary perihelia shows interesting patterns that tell us about the solar system's history. There's a deficit of comets with perihelia near Jupiter's orbit, evidence of the giant planet's role as the solar system's vacuum cleaner, removing comets that venture too close. There's an excess of comets with perihelia just outside Neptune's orbit, suggesting this is a transition region where Kuiper belt objects begin their evolution into short-period comets. These patterns in orbital elements are like footprints in the sand, evidence of billions of years of gravitational sculpting by the planets. Cometary orbits also evolve through non-gravitational forces. As a comet sublimates near the Sun, jets of gas act like tiny rockets, pushing the nucleus and gradually changing its orbit. This effect, called the Yarkovsky effect for asteroids and simply non-gravitational acceleration for comets, can accumulate over multiple orbits to produce significant changes in a comet's trajectory. The unpredictability of these forces, which depend on the comet's shape, rotation, and composition, adds uncertainty to orbital predictions. A comet might return days earlier or later than predicted based on gravity alone, a reminder that these are not just mathematical points but physical objects with complex behaviors. The retrograde motion of some comets, orbiting the Sun in the opposite direction to the planets, creates particularly interesting dynamics. Retrograde comets have higher relative velocities when they encounter planets, making gravitational assists more effective, but also making capture into short-period orbits less likely. The retrograde orbit of Halley's Comet, the most famous of all periodic comets, means it encounters Earth at a combined velocity of over 60 km per hour per second, one of the highest approach velocities of any periodic comet. This high velocity contributes to the spectacular meteor showers produced when Earth passes through Halley's debris trail. The concept of orbital families reveals hidden connections between seemingly unrelated comets. Comets that fragmented from a common parent body continue to follow similar orbits, gradually spreading out over time but maintaining family resemblances in their orbital elements. The Kreutz sun grazers are the most dramatic example, but other families exist throughout the solar system. Studying these families helps us understand how comets fragment and evolve, and can sometimes allow us to predict when related comets might appear. The Great Comet of 1882 and Comet Ikea-Seki in 1965 were both Kreutz family members, and astronomers expect more spectacular sun grazers from this family in the future. The Jupiter family comets, with orbital periods less than 20 years, represent the end state of orbital evolution for many comets. These objects have been captured by Jupiter's gravity into short-period orbits that keep them in the inner solar system. They're the most frequently observed comets, returning predictably and allowing detailed study over multiple apparitions. But this proximity to the Sun comes at a cost. Jupiter family comets lose material rapidly, developing thick crusts of non-volatile material that eventually shut down their activity. Many near-Earth asteroids are probably extinct cometary nuclei, the dead hearts of once active comets that have lost all their ice. The Tisserand parameter, a mathematical quantity that remains approximately constant even as a comet's orbit changes, provides a powerful tool for classifying comets and understanding their evolution. Named after French astronomer Félix Tisserand, this parameter combines information about a comet's semi-major axis, eccentricity, and inclination into a single number. Comets with Tisserand parameters relative to Jupiter less than 2 are typically from the Oort cloud. while those with values between 2 and 3 are usually Jupiter family comets. This simple number encodes deep information about a comet's dynamical history and likely origin. The Hills cloud, the inner region of the Oort cloud, acts as a crucial intermediary in the orbital evolution of comets. Objects in the Hills cloud are more strongly bound to the Sun than those in the outer Oort cloud, requiring stronger perturbations to send them into the inner solar system, but once perturbed, they're more likely to be captured into short-period orbits rather than ejected to interstellar space. The Hills cloud thus serves as a reservoir that slowly feeds comets into observable orbits, maintaining the population of active comets we see today. Without this reservoir, all the short-period comets would have been exhausted billions of years ago. The galactic tide, the differential gravitational force exerted by the galaxy on different parts of the solar system, provides a gentle but persistent influence on cometary orbits. As the solar system orbits the galactic center, it also oscillates up and down through the galactic plane with a period of about 60 million years. When the solar system is above or below the plane, the galactic tide is strongest, potentially triggering comet showers from the Oort cloud. Some scientists have proposed that these periodic comet showers might correlate with mass extinction events on Earth, though this remains controversial. The idea that our galaxy's gravity might influence life on Earth through its effect on comets is a profound connection between the largest and smallest scales of existence. Computer simulations of cometary dynamics have revealed unexpected behaviors and patterns. Some comets can be temporarily captured as satellites of planets, orbiting Jupiter or Saturn for years or decades before escaping. Others can be exchanged between planets, captured by one and later transferred to another. These complex orbital dances show that the solar system is not a collection of independent orbits, but an interconnected network where energy and angular momentum are constantly being exchanged. Every comet that passes through the inner solar system slightly alters the orbits of the planets, and every planet slightly alters the orbit of every comet. It's a cosmic web of gravitational influences, subtle but significant over geological timescales. The prediction of cometary returns is both a triumph and a limitation of celestial mechanics. For well-observed periodic comets, we can predict their returns years or decades in advance, with precision measured in hours. But for long-period comets, uncertainty grows rapidly with time. A comet predicted to return in 1,000 years might arrive decades early or late due to perturbations we can't fully account for. And for comets returning after millions of years, prediction becomes essentially impossible. We can only wait and watch, knowing that somewhere in the darkness, ancient visitors are falling toward the sun, carrying their secrets from the edge of the solar system. The concept of orbital chaos adds a philosophical dimension to our understanding of comets. In a chaotic system, arbitrarily small differences in initial conditions lead to dramatically different outcomes. This means that even with perfect knowledge of the laws of physics, long-term prediction becomes impossible because we can never know initial conditions with infinite precision. Cometary orbits, especially those that closely encounter planets, can be chaotic. This fundamental unpredictability isn't a failure of our theories, but a deep property of the universe itself. The future trajectories of comets, like the future of complex systems in general, remain fundamentally open, full of possibilities that can't be precisely predicted. As we observe the orbital ballet of comets through the solar system, we're reminded that these trajectories are not just abstract mathematical curves, but the paths of real objects carrying real material through space. Every orbit is a story of forces and influences accumulated over billions of years. Every perihelion passage is a test of a comet's structural integrity. Every planetary encounter is an opportunity for orbital evolution. The orbits of comets connect the outer darkness of the Oort cloud to the inner warmth of the terrestrial planets, creating a transportation network that has been operating since the solar system began. The study of cometary orbits also reveals the solar system's future. As the Sun evolves and eventually becomes a red giant billions of years from now, the orbits of comets will change dramatically. The increased solar radiation will activate comets at greater distances, potentially creating a spectacular display of cometary activity throughout the solar system. Eventually, as the Sun sheds its outer layers and contracts to become a white dwarf, many comets will be lost to interstellar space, their orbits no longer bound by the diminished solar gravity. The Oort cloud will slowly disperse, its comets becoming interstellar travelers, carrying the memory of our solar system to the cosmos. But that distant future is almost incomprehensibly far away. For now, comets continue their ancient orbits, following paths laid down by gravity and chance billions of years ago. Each comet we observe is following a trajectory that connects us to the deep past and the far future, a thread in the cosmic tapestry that weaves together space and time. When we calculate a comet's orbit, we're reading a story written in the language of mathematics, a story that began with the formation of the solar system and will continue until the last comet makes its final passage around whatever remains of our Sun. The intersection of chemistry and orbital dynamics reveals the full complexity of cometary science. A comet's orbit determines its thermal history, which determines its chemical evolution. The chemistry determines the comet's activity, which through non-gravitational forces influences its orbit. This feedback between composition and dynamics creates a rich, complex system that we're only beginning to understand. Every comet is both a chemical laboratory and a gravitational test particle, simultaneously telling us about the composition of the early solar system and the dynamical processes that have shaped it over billions of years. As we contemplate these cosmic trajectories and molecular inventories, we're really contemplating our own cosmic heritage. The water in our bodies, the carbon in our DNA, the iron in our blood, all have cosmic histories that might include passage through comets. We are made of material that has travelled vast distances through space, following orbits as precise and beautiful as those of the comets we observe today. In studying comets, we're studying our own origins, tracing the paths that matter took to become us. The distinction between observer and observed begins to blur when we realize that we are made of the same cosmic material, following our own orbital path through space, participants in the same gravitational dance that governs comets. The cosmic dance of comets through our solar system is not merely a physical phenomenon occurring in the cold vacuum of space. It is also a deeply human story, one that has shaped our cultures, our sciences, and our understanding of our place in the universe. For as long as humans have looked up at the night sky, we have been watching, recording, and trying to understand these celestial visitors. The appearance of a bright comet has marked pivotal moments in human history, inspired great works of art and literature, and driven some of the most important advances in our understanding of the cosmos. When we trace the history of comet observation, we're really tracing the history of human curiosity itself, our eternal desire to understand the lights that move across the darkness above us. Consider the first humans who saw a comet. We don't know who they were or when they lived, but we can imagine their experience. Perhaps it was a small group of our ancestors, huddled around a fire on an African plain hundreds of thousands of years ago. As darkness fell and the stars emerged, someone noticed something different in the sky. A fuzzy star with a tail, unlike anything they had seen before. What did they think? What stories did they tell? We can never know for certain, but we can be sure that this sight stirred something deep within them, the same mixture of fear and wonder that comets have evoked throughout human history. That moment of observation, repeated countless times by countless humans over millennia, represents one of the fundamental human experiences encountering the unknown and trying to make sense of it. The earliest recorded observations of comets come from ancient China, where court astronomers kept meticulous records of celestial phenomena for over 2,000 years. The Chinese called comets broom stars or guest stars, and their appearance was considered significant enough to warrant immediate reporting to the emperor. The Han Dynasty silk texts, dating from around 300 BCE, contain detailed descriptions of cometary appearances, including notes on their colour, brightness, and the direction of their tails. These ancient astronomers understood that comets were temporary phenomena, appearing and disappearing according to patterns they couldn't quite grasp. They noted that comets always pointed their tails away from the sun, an observation that wouldn't be explained scientifically for another 2,000 years. In ancient Babylon, priest astronomers recorded cometary appearances on cuneiform tablets, incorporating these observations into their sophisticated astronomical calculations. The Babylonians developed mathematical models that could predict the positions of planets with remarkable accuracy. But comets remained unpredictable, appearing without warning and disappearing just as mysteriously. This unpredictability gave comets a special status in Babylonian astronomy and astrology. They were seen as messages from the gods, omens whose meaning had to be carefully interpreted. A comet appearing in a particular constellation might foretell the death of a king, the outcome of a battle, or the success of the harvest. These interpretations weren't arbitrary, but were based on centuries of accumulated observations, attempts to find patterns in the seemingly random appearances of comets. The ancient Greeks brought a different perspective to cometary observation. While some Greek philosophers, like Aristotle, believed comets were atmospheric phenomena, others recognized them as celestial objects. Apollonius of Mindus, writing in the 1st century BCE, suggested that comets were planets that only became visible when they approached Earth. Seneca, the Roman philosopher, went even further, predicting that someday someone would explain the paths of comets and why they appeared when they did. His prediction wouldn't be fulfilled for another 1,600 years, but it represents an important shift in thinking about comets, from supernatural omens to natural phenomena that could potentially be understood through observation and reason. Medieval Islamic astronomers made crucial contributions to cometary science during Europe's Dark Ages. Astronomers like Abd al-Rahman al-Sufi carefully observed and recorded comets, noting their positions relative to the stars and tracking their movements across the sky. Islamic astronomers were particularly interested in the physical nature of comets. Some proposed that comets were collections of planets that appeared close together in the sky. Others suggested they were atmospheric phenomena caused by the conjunction of planets. While these theories were incorrect, they represent serious attempts to understand comets through natural rather than supernatural explanations. The detailed observations made by Islamic astronomers would later prove invaluable to European astronomers trying to understand cometary orbits. The Great Comet of 1066, which appeared just before the Battle of Hastings, marks a turning point in the cultural history of comets. This comet, later identified as Halley's Comet, was seen across Europe and interpreted differently by different cultures. To the Anglo-Saxons, it was an evil omen foretelling disaster. To the Normans, it was a good sign, predicting victory. The comet appears in the Bayeux Tapestry, one of the most famous medieval artworks, with the inscription, "These men marvel at the star." This appearance of Halley's Comet demonstrates how the same celestial phenomenon could be interpreted in completely different ways depending on one's cultural context and political position. The comet itself was indifferent to human affairs, following its orbit as it had for millions of years, but humans invested it with meaning, made it part of their stories, used it to understand and explain their world. The Renaissance brought new tools and new ways of thinking about comets. The invention of the telescope in the early 1600s revolutionized cometary observation, allowing astronomers to see details invisible to the naked eye. Galileo observed comets through his telescope and engaged in heated debates about their nature. Tycho Brahe's careful observations of the Great Comet of 1577 proved that it was farther away than the Moon, definitively establishing comets as celestial rather than atmospheric phenomena. This was a crucial discovery that challenged the prevailing Aristotelian worldview and paved the way for a new understanding of the cosmos. But it was Isaac Newton and Edmund Halley who truly revolutionized our understanding of comets. Newton's law of universal gravitation provided the mathematical framework for understanding cometary orbits. Halley applied Newton's methods to historical comet observations and made a stunning discovery. The comets of 1531, 1607 and 1682 were actually the same object, returning on a regular 76-year orbit. He predicted the comet would return in 1758, and when it did, appearing exactly as predicted, it marked one of the greatest triumphs in the history of science. For the first time, humans could predict the return of a comet. The mysterious had become mathematical, the unpredictable had become predictable, and comets had transformed from supernatural omens to natural phenomena governed by the same laws that controlled the planets. The successful prediction of Halley's comet's return had profound implications beyond astronomy. It validated Newton's theory of gravitation, demonstrated the power of mathematical physics, and showed that the universe operated according to discoverable laws. This success contributed to the Enlightenment worldview that nature was rational and comprehensible, that through observation and reason, humans could understand and predict natural phenomena. Comets, which had once been symbols of the mysterious and uncontrollable, became symbols of the triumph of human reason over superstition. The 19th century saw an explosion in cometary discoveries, driven by improved telescopes and systematic sky surveys. Amateur astronomers played a crucial role in this golden age of comet hunting. Caroline Herschel, the first woman to discover a comet, found 8 comets between 1786 and 1797, earning recognition as one of the leading astronomers of her day. Jean-Louis Pons, a French astronomer, discovered or co-discovered 37 comets, a record that stood for over a century. These discoveries weren't just about adding to catalogues. Each new comet provided data that helped astronomers refine their understanding of orbital mechanics and the structure of the solar system. The Great Comet of 1811 was visible to the naked eye for 260 days, the longest recorded period of visibility for any comet. It appeared during the Napoleonic Wars and was interpreted variously as an omen of Napoleon's victory or defeat. But beyond the superstitious interpretations, astronomers made detailed scientific observations. They noted changes in the comet's brightness and tail structure, observed jets of material erupting from the nucleus, and tracked its position with unprecedented precision. These observations contributed to growing understanding that comets were not solid objects, but collections of smaller particles held together by weak forces. The development of spectroscopy in the mid-19th century opened a new window into cometary composition. By analysing the light from comets, astronomers could determine what molecules were present in their comae and tails. The discovery of organic molecules in comets was particularly significant, suggesting a possible connection between comets and the origin of life on Earth. Each spectroscopic observation added another piece to the puzzle, slowly building a picture of comets as complex chemical laboratories where exotic molecules could form and survive. The Great September Comet of 1882 provided one of the most spectacular cometary displays in recorded history. This sun-grazing comet became bright enough to be visible in daylight, and its nucleus was observed to fragment into several pieces. The comet's tail stretched across much of the sky, and its appearance inspired countless photographs, paintings, and written descriptions. This was one of the first comets to be extensively photographed, marking the beginning of a new era in cometary observation. Photography allowed astronomers to make permanent records of cometary appearances, to measure positions and brightness with greater accuracy, and to share observations with colleagues around the world. The early 20th century brought new technologies and new perspectives to cometary observation. The development of more sensitive photographic plates allowed astronomers to discover fainter comets and track them over longer periods. Radio astronomy, developed during and after World War II, revealed that comets emitted radio waves, opening another observational window. But perhaps the most significant development was the beginning of the space age, which promised the possibility of studying comets up close, beyond the filtering effects of Earth's atmosphere. The return of Halley's Comet in 1910 occurred during a unique period in human history. For the first time, the comet's approach was anticipated not just by astronomers, but by the general public. Newspapers around the world covered the comet's approach, often with sensationalist stories about Earth passing through the comet's tail. When spectroscopic observations revealed the presence of cyanogen, a toxic gas, in the comet's tail, panic spread despite astronomers' assurances that the gas was far too diffuse to pose any danger. Entrepreneurs sold comet pills to protect against the supposed poison, and some people sealed their windows to keep out the noxious vapours. The 1910 appearance of Halley's Comet demonstrated both how far scientific understanding of comets had come and how persistent superstitious fears remained. The space age transformed cometary science from a purely observational to an experimental discipline. The first spacecraft to observe a comet was the International Cometary Explorer, which flew through the tail of comet Giacobini-Zinner in 1985. But it was the armada of spacecraft sent to Halley's Comet in 1986 that truly revolutionized our understanding of comets. The European Space Agency's Giotto probe flew within 600 kilometers of Halley's nucleus, sending back the first close-up images of a cometary nucleus. These images revealed a dark, potato-shaped object about 15 kilometers long, jets of gas and dust, erupting from specific areas on the surface. The nucleus was much darker than expected, reflecting only about 4% of the sunlight that hit it, making it one of the darkest objects in the solar system. The fleet of spacecraft that encountered Halley's Comet in 1986 included contributions from multiple nations, demonstrating how cometary science had become a global endeavour. Japan sent 2 spacecraft, Saki-Geig and Suisei. The Soviet Union sent Vega 1 and Vega 2. The United States repurposed an old solar wind monitor as the International Cometary Explorer. This international cooperation reflected a growing understanding that comets were not national resources, but cosmic phenomena that belonged to all humanity. The data from these missions was shared freely among scientists worldwide, accelerating our understanding of cometary physics and chemistry. Modern ground-based observations have also been transformed by technology. Charge-coupled devices, CCDs, have replaced photographic plates, providing much greater sensitivity and dynamic range. Adaptive optic systems compensate for atmospheric turbulence, providing images nearly as sharp as those from space telescopes. Automated sky surveys scan the heavens every night, discovering comets that would have been missed by human observers. The Catalina Sky Survey, Pan-STARRS, and Atlas are examples of these robotic sentinels, constantly watching for new comets and asteroids. When Atlas discovered Comet Atlas in 2019, it was continuing a tradition of systematic sky-watching that began with ancient Chinese astronomers, but using technology they could never have imagined. Amateur astronomers continue to play a vital role in cometary science, despite the dominance of professional surveys. Many comets are still discovered by dedicated amateurs who know the sky intimately and can spot anything unusual. Japanese amateur astronomers have been particularly successful, discovering dozens of comets in recent decades. The advent of digital cameras and image processing software has made it easier for amateurs to make meaningful contributions to cometary science. When Comet ATLAS began to brighten in early 2020, amateur astronomers around the world tracked its development, contributing observations that helped professional astronomers understand its behaviour. The internet has transformed how cometary observations are shared and discussed. Real-time reporting of observations, instant sharing of images, and online collaboration between observers on different continents have accelerated the pace of cometary science. When Atlas began to fragment, images from observers around the world were combined to create a detailed picture of the breakup process. Social media platforms allow professional and amateur astronomers to communicate directly with the public, sharing the excitement of cometary observations as they happen. The observation of comets has become a participatory activity, with people around the world contributing to our collective understanding. The cultural impact of comets extends far beyond scientific observation. Comets have inspired countless works of art, from ancient cave paintings to modern digital art. They appear in literature from Shakespeare to science fiction, often as symbols of change, doom, or wonder. Musicians have composed pieces inspired by comets, from Handel's Music for the Royal Fireworks, supposedly inspired by a comet, to contemporary electronic music that attempts to capture the sound of the solar wind interacting with cometary ions. Every bright comet generates a wave of creative expression, as humans try to capture and communicate the awe these celestial visitors inspire. The economic impact of cometary observation is often overlooked but significant. The development of technologies for observing comets has led to innovations in optics, electronics, and data processing that have applications far beyond astronomy. The tourism industry benefits when a bright comet appears, as people travel to dark sky sites for better views. The Hale-Bopp comet in 1997 generated an estimated $1 billion in economic activity in the United States alone, from telescope sales to hotel bookings at observing sites. Even Atlas, despite its failure to become a spectacular naked-eye comet, generated economic activity through increased telescope and binocular sales as people hope to observe it. Education about comets has evolved dramatically over the centuries. Where once knowledge of comets was restricted to a small elite of court astronomers and natural philosophers, today information about comets is freely available to anyone with internet access. Planetariums and science museums create shows about comets, helping the public understand these cosmic visitors. Online courses and educational videos make it possible for anyone to learn about cometary science at their own pace. When a new comet is discovered, educational institutions quickly incorporate it into their curricula, using the excitement of a current event to teach principles of physics, chemistry, and astronomy. The psychological impact of observing comets reveals something fundamental about human nature. The appearance of a bright comet can inspire a sense of wonder that transcends cultural and linguistic boundaries. People who normally never look at the night sky find themselves drawn outside to observe a comet. This shared experience of wonder creates temporary communities of observers, united by their common experience of witnessing something beautiful and transient. The observation of Atlas, even though it never became the spectacular sight some hoped for, still brought together thousands of people worldwide who shared images, observations, and their sense of disappointment when it fragmented. The role of comets in astrobiology has become increasingly important, as we've discovered the complex organic chemistry they contain. The idea that comets might have delivered the building blocks of life to Earth has moved from speculation to a serious scientific hypothesis. Every comet we observe potentially carries clues about the origin of life, not just on Earth, but throughout the universe. When we watch a comet like a TLAS dissolve near the Sun, we're watching the kind of process that might have delivered organic molecules to the early Earth, setting the stage for the emergence of life. This connection between comets and life adds a profound dimension to cometary observation, transforming it from simple sky watching to an investigation of our deepest origins. The technological challenges of observing comets have driven innovation in multiple fields. Tracking a faint comet requires sensitive detectors and sophisticated image processing. Predicting a comet's brightness involves complex models of sublimation and dust production. Analyzing cometary spectra requires understanding molecular physics and chemistry. Each challenge overcome in cometary observation advances our technological capabilities in ways that benefit other fields. The image processing techniques developed for enhancing comet images have applications in medical imaging. The orbital calculation methods refined for comets help track satellites and space debris. The spectroscopic analysis techniques used on comets contribute to environmental monitoring on Earth. The philosophical implications of cometary observation touch on fundamental questions about humanity's place in the universe. When we observe a comet, we're looking at an object that existed long before humans evolved and will likely exist long after we're gone. This perspective can be humbling, reminding us of our cosmic insignificance. But it can also be empowering, demonstrating that despite our brief existence, we've developed the ability to understand and predict cosmic phenomena. The successful observation and analysis of comets like ATLAS shows that consciousness, however fleeting, can comprehend the unconscious cosmos. The future of cometary observation promises even more exciting discoveries. Next-generation telescopes like the Vera Rubin Observatory will discover thousands of new comets, including many from the outer Oort cloud that have never before entered the inner solar system. Space missions are being planned to return samples from cometary nuclei, allowing detailed laboratory analysis of pristine solar system material. Some visionaries even propose capturing small comets and bringing them to Earth orbit for study and possibly resource extraction. The water and organic molecules in comets could potentially support future space exploration, turning these cosmic wanderers into refueling stations for interplanetary travel. Virtual and augmented reality technologies are beginning to transform how we experience cometary observations. Instead of simply looking at images on a screen, we can now immerse ourselves in three-dimensional models of comets, fly through their tails, and experience what it would be like to stand on their surfaces. These technologies make cometary science more accessible and engaging, especially for young people who might be inspired to pursue careers in astronomy. When the next bright comet appears, millions of people will be able to experience it through VR headsets, seeing it as if they were floating in space alongside it. The development of artificial intelligence and machine learning is revolutionizing cometary observation and analysis. AI systems can now automatically detect comets in survey images, track their brightness evolution, and even predict their behavior based on patterns learned from historical data. These systems can process vast amounts of observational data far faster than human astronomers, freeing scientists to focus on interpretation and understanding rather than routine analysis. When Atlas began to fragment, AI systems helped identify and track the individual fragments, providing insights that might have been missed by human observers alone. The democratization of cometary observation continues to accelerate. High-quality telescopes and cameras are more affordable than ever. Software for processing astronomical images is freely available. Online databases provide access to professional observations and historical records. Anyone with interest and dedication can contribute to cometary science, regardless of their formal education or geographic location. This democratization is creating a global community of comet observers, united by their shared passion for these cosmic visitors. When Atlas appeared, observers from every continent contributed to our understanding of its behavior, demonstrating that cometary science has truly become a global endeavor. The intersection of indigenous knowledge and modern cometary science offers new perspectives on these celestial phenomena. Many indigenous cultures have rich traditions of comet observation and interpretation that predate Western astronomy by centuries or millennia. Aboriginal Australians, for example, have oral traditions describing comets that stretch back tens of thousands of years. These traditions often contain accurate observations of cometary behavior encoded in mythological language. By combining indigenous knowledge with modern science, we can gain a more complete understanding of how comets have influenced human culture and potentially recover observations of historical comets not recorded in Western sources. Climate science has found unexpected connections to cometary observation. The dust and gas released by comets can affect Earth's upper atmosphere, potentially influencing weather patterns. Major cometary impacts in the past have certainly affected climate, and understanding these effects helps us better understand current climate change. The techniques developed for analyzing cometary atmospheres are now being applied to studying Earth's atmosphere and those of other planets. The interdisciplinary nature of modern science means that advances in cometary observation can have unexpected benefits for seemingly unrelated fields. The search for potentially hazardous comets has become an important aspect of planetary defense. While most comets pose no threat to Earth, a large comet on a collision course could cause catastrophic damage. The same surveys that discovered ATLAS are constantly watching for objects that might threaten Earth. International cooperation in this area is essential, as a cometary impact would affect all of humanity regardless of national boundaries. The observation of comets has thus evolved from satisfying curiosity to potentially saving civilization, adding urgency to what was once purely academic research. The artistic and cultural legacy of cometary observation continues to evolve. Contemporary artists use data from cometary observations to create visualizations that blur the line between science and art. Musicians compose pieces based on the orbital periods of comets or the frequencies of molecules detected in their spectra. Writers use comets as metaphors for transformation, impermanence, and the connection between Earth and cosmos. Every comet that appears generates new cultural expressions, adding to the rich tapestry of human responses to these celestial visitors. Atlas, despite its modest appearance, inspired numerous artistic works, from paintings to poems to musical compositions. The educational value of comets extends beyond formal astronomy education. Comets provide accessible examples of many scientific principles: gravity, thermodynamics, chemistry, and even quantum mechanics. The excitement generated by a new comet can motivate students to learn mathematics to calculate orbits, chemistry to understand sublimation, and physics to comprehend non-gravitational forces. Teachers worldwide use comets as hooks to engage students in science, capitalizing on the natural wonder these objects inspire. The story of Atlas, with its unexpected brightening and disappointing fragmentation, provides lessons about the nature of scientific prediction and the importance of continued observation, even when outcomes don't match expectations. Moving deeper into the contemplation of impermanence and cosmic cycles, we find that comets serve as profound teachers about the nature of existence itself. Every comet that graces our skies is simultaneously ancient and ephemeral, carrying within its frozen heart materials that have existed since the birth of the solar system, yet manifesting as a visible phenomenon for only a brief moment in cosmic time. This duality speaks to something fundamental about the universe and our place within it. When we observe a comet dissolving in the solar wind, we're witnessing a meditation on transience that has been playing out for billions of years, long before humans existed to contemplate it. The fragmentation of Atlas in April 2020 was not a failure or a disappointment from a cosmic perspective. It was simply the latest iteration of a process that has been occurring throughout the solar system's history. Comets have been forming, approaching the Sun, and dissolving for 4.6 billion years. Each dissolution returns material to the interplanetary medium, where it can be recycled into new objects. The atoms that composed Atlas don't cease to exist when the comet fragments. They simply transition to a new phase of their eternal journey through space and time. This process of formation, dissolution, and reformation is the heartbeat of the cosmos, a rhythm that encompasses everything from subatomic particles to galaxy clusters. The human tendency to see cometary fragmentation as disappointing reveals our deep-seated desire for permanence in an impermanent universe. We wanted Atlas to survive its solar passage, to become the spectacular comet that predictions suggested it might be. When it fragmented instead, many observers felt a sense of loss, but this emotional response, while natural, misses the deeper beauty of what occurred. The fragmentation of Atlas was not a destruction, but a transformation, not an ending, but a transition. The comet didn't fail, it simply followed the physical laws that govern all matter in the universe. In its dissolution, Atlas demonstrated the same principles that govern our own existence. Nothing lasts forever, but nothing is ever truly destroyed. The timescales involved in cometary evolution provide a powerful perspective on human concerns. Atlas likely formed 4.6 billion years ago and spent most of that time in the outer darkness of the Oort cloud. Its final journey to the Sun took hundreds of thousands or millions of years. Its visible appearance lasted a few months. Its fragmentation occurred over a few weeks. These nested timescales, from billions of years to weeks, encompass the entire range of temporal experience. Human lives, human civilizations, even the entire history of our species, occupy just a tiny fraction of a comet's existence. Yet in that brief moment when our timescales intersect, when a comet becomes visible in our skies, we have the opportunity to witness and contemplate processes that connect us to the deepest history of the cosmos. The beauty of impermanence is not despite its transient nature, but because of it. A comet is beautiful precisely because it doesn't last forever. Its tail, stretching millions of miles through space, exists only because the comet is evaporating, losing part of itself to create the spectacle we observe. If comets were permanent, unchanging objects, they would be merely another type of asteroid, important for science but lacking the poetic power that makes them so compelling. The temporary nature of cometary displays makes them precious, worth staying up late to observe, worth remembering for a lifetime. Atlas, even in its fragmentation, created moments of beauty that were all the more meaningful because they were fleeting. The philosophical implications of cometary impermanence extend to our understanding of value and meaning. In a universe where everything is temporary, where even the stars will eventually die and the galaxies disperse, what gives anything meaning? Comets suggest an answer. Meaning doesn't require permanence. The brief appearance of a comet can inspire wonder, advance scientific knowledge, and create lasting memories, even though the comet itself dissolves. The temporary can have permanent effects. The fleeting can create the eternal. Atlas no longer exists as a coherent object, but its observation advanced our understanding of cometary fragmentation, inspired countless people to look up at the night sky, and added to the accumulated knowledge that will benefit future generations. The Buddhist concept of impermanence finds a perfect expression in cometary phenomena. Nothing is permanent, everything is in constant flux, and attachment to permanent forms leads to suffering. A comet embodies these principles in its very nature. It's constantly changing, losing material with each moment near the sun, its appearance different each night. Those who became attached to the idea of Atlas as a great comet experienced disappointment when it fragmented. But those who appreciated it for what it was, a temporary visitor offering a brief glimpse of cosmic processes, found beauty and meaning in its appearance regardless of its ultimate fate. The comet becomes a teacher, demonstrating through its own existence the principles that Buddhist philosophy has articulated for millennia. The cycles of cometary orbits represent another aspect of cosmic rhythm. Short-period comets return regularly, like Halley's Comet every 76 years, creating a multi-generational drumbeat that connects human lives across centuries. Long-period comets like ATLAS might return after hundreds of thousands of years, their cycles so vast that they encompass the entire history of our species. These different orbital periods create a complex temporal symphony, with each comet contributing its own frequency to the cosmic composition. We experience only a tiny fragment of this symphony during our lives, but knowing it exists, knowing that comets will continue their orbits long after we're gone, provides a sense of continuity that transcends individual existence. The relationship between creation and destruction in cometary evolution mirrors similar processes throughout the universe. When a comet fragments, it might seem like destruction, but it's also creation. The fragments become new comets, each with its own orbit and future. The dust released enriches the interplanetary medium. The gases contribute to the solar wind. The organic molecules might eventually find their way to planetary surfaces where they could participate in biological processes. What appears as death from one perspective is birth from another. Atlas died as a single comet but was reborn as multiple fragments, each carrying forward part of the original comet's legacy. The concept of cosmic recycling embodied by comets provides a powerful metaphor for sustainability and environmental thinking. In the cosmos, nothing is waste. Everything is resource for future processes. The material that composes comets has been recycled countless times, from interstellar gas to comet to planetary material and back again. This cosmic recycling has been operating for billions of years without depleting resources or accumulating waste. Earth's biosphere operates on similar principles, with materials constantly recycled through geological and biological processes. Comets remind us that we're part of this larger recycling system, that the atoms in our bodies have cosmic histories and cosmic futures. The unpredictability of cometary behavior, exemplified by Atlas's unexpected fragmentation, teaches humility about our ability to control and predict natural phenomena. Despite our sophisticated models and powerful computers, we couldn't predict exactly when or how Atlas would fragment. This uncertainty isn't a failure of science, but a recognition of the complexity of natural systems. Comets, like weather systems, ecosystems, and many other natural phenomena, exhibit sensitive dependence on initial conditions that makes long-term prediction impossible. This fundamental unpredictability requires us to remain flexible, to adapt our expectations to reality, rather than expecting reality to conform to our predictions. The role of patience in cometary observation reflects a virtue increasingly rare in our accelerated world. Observing a comet requires patience on multiple timescales. We must wait years or decades or centuries for a comet to return. We must wait months for it to brighten as it approaches the sun. We must wait hours for it to rise above the horizon. We must wait minutes for our eyes to adapt to the darkness. This enforced patience is a gift, slowing us down, connecting us to natural rhythms that operate on timescales longer than news cycles or social media updates. The observation of Atlas required patience from thousands of observers worldwide, and even though the comet didn't meet expectations, the practice of patient observation was valuable in itself. The community that forms around cometary observation demonstrates humanity's capacity for cooperation in pursuit of knowledge and beauty. When Atlas appeared, observers from different countries, cultures, and backgrounds united in their common interest. They shared observations, offered advice, expressed excitement and disappointment together. This temporary community, formed around a temporary celestial event, shows how cosmic phenomena can bring humans together across divisions that seem important from Earth, but insignificant from space. The comet doesn't care about national boundaries, political ideologies, or economic systems. It appears for all humanity, and in observing it, we remember our common heritage as inhabitants of Earth. The question of meaning in a universe of impermanent phenomena is one that comets help us explore. If everything is temporary, if all structures eventually dissolve, what gives life meaning? Comets suggest that meaning might not come from permanence, but from participation in the cosmic process. When we observe a comet, we're participating in a moment of cosmic evolution. When we share that observation with others, we're creating meaning through connection. When we use the observation to advance knowledge, we're contributing to humanity's collective understanding. The meaning isn't in the comet itself, but in our engagement with it, our response to it, our integration of it into our understanding of ourselves and our universe. The aesthetic dimension of cometary observation reveals the human capacity to find beauty in natural phenomena. A comet is beautiful not because it was designed to be beautiful, but because human consciousness has evolved the capacity to perceive beauty in certain forms, movements, and lights. The curved tail of a comet, the gradual brightening as it approaches the sun, the delicate structure of dust and gas, all these appeal to aesthetic sensibilities that evolved for entirely different purposes, but now allow us to appreciate cosmic phenomena. When we find a comet beautiful, or experiencing the universe appreciating itself through conscious observers. Atlas, even in its fragmented state, created moments of beauty that existed only in the intersection of cosmic phenomenon and human perception. The metaphorical power of comets in human thought reflects our tendency to use cosmic phenomena to understand human experience. Comets have been metaphors for sudden change, for portents of the future, for the intersection of the eternal and the temporary. In literature, comets often appear at moments of transformation, their celestial motion paralleling character development or plot evolution. In personal narratives, people often remember where they were when they saw a particular comet, the celestial event becoming a marker in their life story. Atlas, appearing during a global pandemic, became for many a metaphor for the unpredictability of 2020, its fragmentation paralleling the disruption of normal life. The technological mediation of modern cometary observation raises questions about authentic experience. Most people who observed Atlas did so through photographs on screens rather than direct visual observation. Is viewing a high-resolution image of a comet on a computer monitor the same as seeing it with your own eyes through a telescope? The image might show more detail, more colour, more structure than the eye could ever perceive. But something is lost in the mediation, the direct connection between observer and cosmos that has characterised human astronomy for millennia. This tension between technologically enhanced observation and direct experience reflects broader questions about how technology mediates our relationship with nature. The democratization of information about comets has transformed how we collectively experience these events. When Atlas was discovered, information about it spread globally within hours. Orbital elements were published online, allowing anyone with appropriate software to predict where the comet would appear in their sky. Images were shared on social media, creating a global conversation about the comet. This rapid, democratic distribution of information is unprecedented in human history. For most of our species' existence, comet observations were local events, known only to those who happened to see them. Now, a comet discovered by a robotic telescope in Hawaii can be observed by someone in Europe within days, using information transmitted instantly across the globe. The economic dimensions of cometary observation extend beyond direct costs and benefits to include broader questions about resource allocation and scientific priorities. The telescopes that discovered ATLAS cost millions of dollars to build and operate. The time spent observing ATLAS could have been spent on other scientific projects. Was this investment worthwhile for a comet that ultimately disappointed public expectations? From a narrow economic perspective, perhaps not. But from a broader perspective that includes educational value, public engagement with science, technological development, and contribution to long-term knowledge, the investment was justified. Every comet we observe adds to our understanding, and we can't know in advance which observations will prove most valuable. The cultural memory of comets persists long after the comets themselves have faded. Halley's Comet appears in historical records spanning millennia, allowing us to trace its influence on human culture across centuries. The Great Comet of 1811 appears in literature, art, and wine labels, its memory preserved in cultural artifacts. Even failed comets like Kohoutek in 1973, which didn't live up to expectations, remain in cultural memory as cautionary tales about prediction and hype. Atlas will likely be remembered not as a great comet, but as the comet that might have been, the comet that fragmented during the pandemic, the comet that reminded us of the uncertainty inherent in natural phenomena. The future of human-comet interaction promises new forms of engagement beyond passive observation. Missions are being planned to mine comets for water and other resources. Some visionaries imagine capturing small comets and using them as interplanetary gas stations. Others propose using cometary material to terraform Mars or provide radiation shielding for space habitats. These plans transform comets from objects of observation to resources for exploitation, raising ethical questions about humanity's relationship with cosmic phenomena Do we have the right to mine comets? Who owns cometary resources? How do we balance scientific study with commercial exploitation? These questions will become increasingly important as our technological capabilities expand. The possibility of comet-borne life or its precursors adds another dimension to our relationship with these cosmic wanderers. If comets delivered the building blocks of life to Earth, might they also deliver them to other worlds? Could life itself survive in cometary ice, dormant for millions of years, awakening when the comet approaches a star? These possibilities, while speculative, transform every comet observation into a potential encounter with life or its precursors. When Atlas dissolved near the Sun, it released organic molecules that had been preserved for billions of years. Some of these molecules might eventually find their way to Earth or other planets, potentially contributing to biological processes. In this view, comets are not just passive objects but active participants in the spread of life through the cosmos. The symbolic power of comets in human consciousness seems unlikely to diminish, even as our scientific understanding increases. If anything, knowing more about comets makes them more rather than less wondrous. Understanding that Atlas was a mountain of ice that travelled for millions of years from the edge of the solar system doesn't diminish its impact on human imagination. Instead, it adds layers of meaning, connecting us to cosmic processes and timescales that dwarf human experience. The tension between scientific understanding and emotional response enriches rather than diminishes our experience of comets. We can simultaneously know that a comet is a dirty snowball following predictable laws of physics and experience it as a wonder that takes our breath away. The role of comets in expanding human consciousness beyond Earth reflects their importance not just as scientific objects, but as catalysts for cosmic awareness. Every person who observes a comet, who takes a moment to contemplate this visitor from the outer solar system, expands their awareness beyond the immediate concerns of daily life. This expansion of consciousness, multiplied across millions of observers, represents a collective evolution of human awareness. We are a species becoming aware of its cosmic context, and comets are among the phenomena that facilitate this awareness. Atlas, despite its brief appearance and fragmentation, contributed to this collective expansion of consciousness, reminding thousands of people to look up, to wonder, to remember their place in the cosmos. The ultimate question raised by our observation of comets might not be whether they're watching us, but what it means that we're watching them. The fact that the universe has evolved conscious beings capable of observing and understanding comets is perhaps more remarkable than the comets themselves. We are the universe becoming aware of itself, using comets as mirrors to see our own cosmic nature. When we observe a comet like ATLAS, we're not separate from the cosmic process, but part of it, matter observing matter, the cosmos contemplating itself through human eyes and minds. This reflexive observation, this cosmic self-awareness, might be the most profound aspect of the human-comet relationship. As we approach the end of our contemplation, we return to the question that began our journey. Was Atlas watching our planet? In the literal sense, of course not. Atlas had no eyes, no consciousness, no awareness. It was a collection of ice and rock following the laws of physics, indifferent to Earth and its inhabitants. But in a deeper sense, through ATLAS, the universe was watching itself. The atoms that composed ATLAS were forged in stars that died billions of years ago. These atoms assembled into a comet that preserved them for the age of the solar system. When Atlas approached the Sun, these atoms were released, some perhaps destined to become part of future planets, future life, future observers. In this cosmic recycling, in this eternal transformation of matter and energy, there is a kind of watching, a kind of awareness that transcends individual consciousness. The journey of Atlas from formation to dissolution encompasses the entire history of our solar system. In its frozen nucleus, it carried information about conditions 4.6 billion years ago. In its orbit, it traced the gravitational architecture of the solar system. In its composition, it preserved the chemical heritage of the interstellar medium. In its fragmentation, it demonstrated the processes that have been shaping comets throughout cosmic history. And in our observation of it, it catalyzed human consciousness, inspiring wonder, advancing knowledge, creating connections between observers across the globe. Atlas was simultaneously messenger and message, observer and observed, teacher and lesson. The legacy of ATLAS extends beyond its brief appearance in our skies. Every person who observed it, who thought about it, who was inspired by it, carries forward its influence. Children who learned about ATLAS might grow up to become astronomers. Artists inspired by ATLAS might create works that inspire others. Scientists who studied ATLAS will apply their knowledge to future comets. The ripples of Atlas's passage through the inner solar system continue to propagate through human culture and consciousness, influences that will persist long after the comet's fragments have dispersed. In this way, Atlas achieves a kind of immortality, not as a physical object, but as an idea, a memory, an inspiration. The question of cosmic observation and awareness touches on the deepest mysteries of existence. In a universe governed by physical laws, where does consciousness come from? How does matter become aware of itself? What does it mean for the universe to observe itself through conscious beings? Comets like ATLAS don't answer these questions, but they provide a context for contemplating them. They remind us that we are part of a vast, ancient, ongoing cosmic process. They show us that the distinction between observer and observed is not as clear as we might think. They demonstrate that the universe is not a collection of separate objects, but an interconnected whole in which every part influences every other part. As we drift towards sleep, contemplating the journey of Atlas and our own cosmic journey, we might find comfort in the continuity of cosmic processes. Comets will continue to fall from the Oort cloud long after we're gone. Future observers will experience the same wonder we feel when a bright comet appears. The atoms that compose us will eventually be recycled into new forms, perhaps even new comets. We are temporary arrangements of eternal matter, brief observers of endless processes, fleeting consciousness in an ancient cosmos. This perspective might seem to diminish our importance, but it can also be profoundly liberating. We don't have to be permanent to be meaningful. We don't have to last forever to make a difference. Like Atlas, we can shine briefly but brilliantly, contributing our small part to the cosmic story. The silence of space through which Atlas travelled is not empty but pregnant with possibility. In that apparent void, particles stream from the sun, magnetic fields twist and spiral, gravitational waves ripple from distant cosmic events. The space between objects is as much a part of the universe as the objects themselves. When we observe a comet, we're seeing not just the comet, but its interaction with this supposed emptiness, the way it responds to solar radiation, solar wind, magnetic fields, gravitational gradients. The comet reveals the invisible forces that permeate space, making visible what would otherwise be hidden. Atlas, in its journey and dissolution, mapped the invisible architecture of the inner solar system, revealing through its response the forces that shape all cosmic motion. The question, was Atlas watching our planet, ultimately transforms into a meditation on the nature of observation, consciousness, and our place in the cosmos. Through ATLAS, we've explored the vast reservoir of the Oort cloud, the complex chemistry of cometary ices, the precise mathematics of orbital motion. We've traced the history of human comet observation from ancient times to the present day. We've contemplated impermanence, beauty, and meaning in a universe of constant change. And through it all, we've been watching ourselves, seeing in Atlas a mirror of our own cosmic nature, our own journey through space and time. As this contemplation draws to a close, we're left not with answers, but with a deeper appreciation of the questions. The universe remains mysterious, full of wonders we've yet to discover, processes we've yet to understand, beauties we've yet to appreciate. Every comet that appears reminds us of this mystery, this ongoing revelation of cosmic complexity and elegance. Atlas was just one comet among trillions, its appearance just one moment in cosmic history. But through our observation and contemplation of it, it became part of human consciousness, part of our collective understanding of our place in the universe. The final lesson of ATLAS might be that the most important questions are not those that can be definitively answered, but those that inspire continued wonder and investigation. Was Atlas watching our planet? The question invites us to think about the nature of observation, the relationship between consciousness and cosmos, the meaning of existence in an impermanent universe. These are not questions with simple answers, but invitations to deeper contemplation, to continued observation, to ongoing wonder. In asking these questions, in pursuing these investigations, in maintaining this wonder, we fulfill our role as the universe's way of understanding itself. The fragments of Atlas continue their journey through the solar system, too faint to observe but still real, still following their orbits, still participating in the cosmic dance. Some may return to the inner solar system in future centuries, perhaps to be observed by future generations who will wonder about their origin and meaning. Others may be ejected from the solar system, becoming interstellar travelers carrying information about our cosmic neighborhood to distant stars. Still, others may collide with planets or moons, delivering their cargo of water and organic molecules to worlds we can only imagine. The story of ATLAS continues, even though the comet itself is gone, its influence propagating through space and time in ways we can trace and ways we cannot. In the end, the question of whether Atlas was watching our planet becomes less important than the fact that we were watching Atlas, that we continue to watch the skies, that we maintain our curiosity about the cosmos despite the challenges and distractions of terrestrial life. This watching, this curiosity, this wonder is perhaps what makes us most human. We are the species that looks up, that asks questions, that seeks to understand our place in the universe. Comets like ATLAS give us opportunities to exercise these capacities, to connect with something larger than ourselves, to participate in the ancient dialogue between Earth and cosmos. As you drift towards sleep, perhaps you can imagine yourself as part of this cosmic conversation, a conscious observer in an unconscious universe, a temporary arrangement of eternal matter capable of appreciating beauty, understanding patterns, and finding meaning in the dance of celestial bodies. The same forces that governed Atlas govern you. The same atoms that composed ATLAS compose you. You're not separate from the cosmic story, but an integral part of it, a moment of awareness in the vast unfolding of space and time. And in this recognition, in this connection to the cosmos through contemplation of a comet, perhaps you can find the peace that comes from knowing your place in the universe. Temporary but meaningful, brief but beautiful, a flash of consciousness in the eternal night.